we're going to do it online, and we have the great honor of having Pablo Herrero giving the opening talk on Twisted Bilayer Graphene, which is the main focus of the school. So Pablo, whenever you want.
Thank you very much, Maya, and thank you, Adolfo, and everyone for the invitation. As Maya said, I wish very much I could be there in San Sebastian in person. It's a city I really like, and I hope that soon, maybe next year or so, we will be able to have these events back in person. So I saw a couple of days ago, I noticed that I had to give 3 lectures. I thought it was 1, so it's good always to check, the schedule a few days before you actually have to give the talks. And so what I have decided is that I'm going to be, I'm going to give an introduction today to magic angle graphene. It's also the first talk, and there will be other talks later on in the day, more, with more details. And then I will give another talk tomorrow, which will be about more, more detailed, investigation of the electronic properties of magic angle bilayer graphene. And then I will, on the 3rd day, I will tell you about a new system, which is magic angle tri-layer graphene, 3 layers. Okay, and that will, that will sort of provide an overview of a good fraction of my group activities on this topic. In fact, today I'm going to be telling you not only about magic angle graphene, but also a little bit more general about more quantum matter. Okay, so because this is a summer school, and I think probably there are plenty of students with very diverse backgrounds. Let me give you more of a general introduction, and let me see if I can get my laser pointer here. Okay, good. So, among the most fascinating states of matter that we have in the universe are those where interactions between the individual constituents that make up that matter are very strong. And this is something that happens, in all areas of physics. So you have, for example, the quark gluon plasma state, okay, which is a state of matter that happens a few microseconds, nanoseconds after the Big Bang, and that we can recreate nowadays in, for example, heavy ion collisions, this, at Brookhaven National Laboratory. We also have, for example, different phases of nuclear matter in neutron stars. These are all strongly correlated. This is a, Chandra X-ray observatory picture of a neutron star. And if you go to Wikipedia, you can see that these different phases, they are called nuclear pasta. So they have the lasagna phase, the spaghetti phase, the bucatini phase. As usual, the astrophysicists are very creative with naming things. And these are all strongly correlated. And then perhaps a bit closer to, to my heart are the different topological states of matter, okay, which there are many. For example, if you take a system of 2-dimensional electron gases and you subject it to perpendicular magnetic field, you can enter the fractional quantum Hall regime in which electrons, now become, the quasi-particles now become fractionalized. They acquire a fraction of an electron charge, and they have very interesting topological properties. So if we zoom in a bit more into strongly correlated quantum materials, this is, this includes many classes of materials. Perhaps one of the most studied and most famous are the high temperature superconductors, okay, where in a phase diagram sorry, you can't see the axis here, temperature on the vertical axis, and doping, we have a variety of phases, few of which we have, a very good theoretical understanding of even to this day. Yeah? So in order to set the stage for what I'm going to be telling you about, let's think a bit about, how do we understand, from the electronic transfer point of view, materials? Yeah? If you take single particle band theory, okay, we basically have 2 options. Okay, to see the order, we have 2 options. So if you have a material where you have the density of states here on this axis, this is versus energy, and you have a material which has 2 bands. One of them is fully occupied with electrons, and the next one is fully empty. This is an insulator, okay? This is the band gap of the insulator. We say that this is an insulator because, at zero temperature, all of your carriers are stuck in this band, and even at finite temperature or by applying a voltage, it's hard to get any electrons excited because of the presence of this band gap. Okay, so quasi-particle, you don't have electrons that can transport electricity upon application of a small voltage or some amount of temperature, small temperatures, just room temperature, if this band gap is large enough. On the other hand, if you have a material, with similar density of states, but this time with a Fermi energy which is in the middle of this higher band, so that this higher band is partly occupied. Now you have, at infinitesimally small energies, free energy state, free electron states which are available to conduct electricity when you apply voltage or temperature. Okay, and then we say that this material is a metal. Now, a situation can occur in some materials where you are in a situation which is similar to this one, and you would expect metallic behavior. However, you have insulated behavior due to very strong interaction between your electrons. Yeah, and on those occasions we say that that behavior is that of a correlated insulator. Yeah? So you can be in a situation where your Fermi energy is in the middle of this band, but due to strong electron-electron interactions, there is a gap, which has to do with a many-body gap, okay, that opens in this band, okay, such that this band, this lower band, is fully occupied. This upper band is fully empty. For example, if you were at half filling, okay, and now you see the situation is very reminiscent, very similar to that of the insulator situation, but this gap is a many-body gap. It's not a single particle gap, okay, and that is a correlated insulator. Now, there are many examples of correlated insulators. One which is particularly famous is the MOT insulator, which is believed to be the parent compound of the high temperature cuprate superconductors. Okay? So in the high temperature cuprate superconductors, most of the action takes place in these copper oxygen planes, where in the stoichiometric compound, without doping, there is 1 electron per copper atom, so 1 electron per unit cell, okay? And all of the electrons, due to the strong repulsion between electrons, are stuck in their positions, okay? So this is a correlated insulator. And now an interesting game takes place if you remove a few of those electrons or you dope with holes. Okay? Now your electrons can jump from occupied side to empty sides, but they have to do that in a correlated fashion, okay? Again, because of the penalty for double occupancy. So this behavior is believed to be described by a model, theoretical model called the Hubbard model, okay, which takes into account the finite, hopping between sites, and also the energy penalty U of occupying a site with 2 electrons. Okay? And now I say that we believe that the behavior of cuprates is described by the Hubbard model, because we cannot really solve the Hubbard model even in the simplest case exactly for a large number of electrons. So we do not know how to go from this model to this phase diagram. There's no one-to-one mapping, exactly analytically. Now, the lack of progress or the lack of theoretical understanding, despite decades of research, has led to alternative platforms to investigate the properties of quantum materials. Okay, and one of the most successful is to use, for example, ultra cold atoms in optical lattices. So if you take 2 laser beams, and you shine them, 4 laser beams, you shine them at each other, you can create this periodic potential in which you can load atoms. And there is a tuning knob, something called the Freshwater Resonance, which allows you to tune the interaction between these atoms, such that already back in about almost 20 years ago, the group of Immanuel Bloch was able to tune the system of ultra cold atoms between a multi-insulator state and a superfluid state, okay, for attractive interactions. Then this was done with bosonic atoms, so atoms with integer spin. So this was a realization of the Bose-Hubbard model. Then a few years later, this was done with fermionic atoms in a realization of the Fermi-Hubbard model. And just to give you an idea, the state of the art in this community, at least as of a couple years ago, is that people have been able to realize anti-ferromagnetism in the Fermi-Hubbard model. Okay, so this means that the ultra cold atoms community is beginning to explore this region of the phase diagram. Okay, mode physics, anti-ferromagnetism. They would like to explore the entire phase diagram, in particular, to find D-wave superfluidity in the cold atom systems. However, it is very challenging to go down in temperature to the temperatures needed for this. Okay, they are already working at nanokelvin or hundreds of picokelvin, and they need to go about an order or 2 magnitude lower in temperature to reach this region. That's what they believe. And they although there's no fundamental obstacle to doing so, it is very challenging. So they haven't done that yet. So we have these, two, if you want, traditional platforms to investigate strongly correlated physics. One is the actual quantum materials themselves, okay, with typical lattice scales of a few angstroms. Another one is cold atoms in optical lattices with typical length scale of a micron. And what I want to tell you about today is about a new platform called Moiré quantum matter, where the Moiré length or wavelength is typically of the order of 10 nanometers. So it's about a couple of orders of magnitude in between either of, between these two platforms, associated with this length scale and also energy scales. Okay, so for quantum materials, typical energy scales or temperature scales are 100 to 1,000 Kelvin. For ultra cold atoms, it's 0.1 to 1 nanokelvin. For Moiré quantum matter, is 1 to 10 Kelvin, maybe up to 100 Kelvin. Okay, so it's also a nice intermediate energy scale and very accessible in modern dilution refrigerators, so that we can investigate this and study these systems. So this is, the outline for my talk today. I want to tell you a little bit about 2D materials, Legoland, twistronics, some terms that you may hear about. Then I'll introduce graphene and magic angle graphene superlattices. Then I'll tell you about our observation of correlated insulators and superconductivity. And then I'll tell you a little bit about what has happened since our discovery, and also some interesting, new type of more structures that we're looking at in other materials. So let me start with this. So for about for 17 years or so, we've been investigating the properties of atomically thin 2D materials, crystalline 2D materials, and people were initially just looking at the properties of graphene, and then it became very clear that we could stack these 2D materials on top of each other to create what are known as van der Waals heterostructures. Okay, and that led my friends and colleagues to look at these superlattices and make these analogies with a Legoland. Okay, because of the fact that you can put these materials arbitrarily on top of each other. Now, although this analogy with Legoland is a good one, okay, and it's something which is quite characteristic of 2D materials, I think it's not perhaps the most unique aspect of 2D materials. The most unique aspect of 2D materials, which has no precedent in the history of material science, is the fact that one can do this thing. One can put two two-dimensional crystals, okay, rotated with respect to each other at an arbitrary twist angle of rotation. That's something that could not be done before the advent of 2D materials, and it's something that can be quite, can change dramatically the properties of the materials. So let me tell you a little bit about graphene. So, and I hear my kids, yes, let me just shut the door, sorry. Okay, this is what happens when you give Zoom talks, from home. So graphene is a honeycomb of carbon atoms, okay? All of these atoms are, from the chemical point of view, equivalent. They're all carbon atoms, but from the crystallographic point of view, there are two sublattices, two inequivalent sublattices. They're called the A and B sublattice, or the red and green balls, okay? That's because in order to tile a honeycomb, you need two vectors plus two sublattices, or two. So in a simple quantum mechanical model, and type binding model, one can calculate the electronic structure of electrons in graphene. And here you have it, energy versus momentum in the X and Y direction. And as you can see, this is a very unusual electronic structure. Okay, it's a very famous one, because near the Fermi energy, you have these double cones, which are called Dirac cones, okay, where the relationship between energy and momentum is linear, okay? So graphene is a zero band gap semiconductor, or a semi-metal, with a zero band overlap with linear energy momentum dispersion. In fact, this type of dispersion is more characteristic of ultra-relativistic massless particles. And if you look at the Hamiltonian equation that governs this dynamics of electrons in graphene, it's nothing else but the Dirac equation in 2-dimension for massless particles, okay? Where you can see here, energy is linear in momentum, and where the spinor, which usually in the Dirac equation represents whether the spin of the electron is up or down. Here, in the case of graphene, it's telling you whether the weight of the electron wave function is on the A or B type sublattice. Okay? Now, the other thing that I want you to remember is that there are two inequivalent sets of Dirac cones. They are called the K and the K prime valleys because they are at the K and K prime points, okay, in the reciprocal momentum space. So just remember that electrons in graphene has this fourfold degeneracy: spin up, spin down, valley K prime. Okay, just remember 4. It will appear later on. So what happens if you put graphene on top of graphene and rotate the angle? Okay, a moire pattern forms where the distance between, the moire wavelength, which is the distance between the soccer balls that you see on the screen, okay, is roughly inversely proportional to the twist angle, at least for small twist angles, okay? So now this is what happens in real space. Let's look at what happens in momentum space and hence what happens to the electronic structure. So we have here a single layer of graphene. This is the electronic structure. This is real space. This is the Dirac, the Dirac cone. These are reciprocal space. If your Fermi energy is at some finite value above the Dirac point, then you have these Fermi disks, okay, located at the K and K prime point. Okay, these are the Fermi surfaces. Now, let's put another graphene sheet on top. If these two graphene sheets are perfectly aligned, then the reciprocal spaces are also perfectly aligned. And the Dirac cones of layer 1 and layer 2 of graphene are on top of each other, okay? But if we now rotate by a certain angle, okay, then if we rotate in real space by a certain angle, the reciprocal spaces also rotate by the same angle, okay? So the separation between the Dirac points or Dirac cones of layer 1 and layer 2 of graphene, okay, becomes 2k times sine of theta half, okay? Now, let's, so this means twisting leads to layer Dirac cones separating the momentum space. Now let's start from a relatively, from a small angle of rotation, such that the separation in momentum space is proportional to the rotation angle. And let's have a look at what happens, okay? So here I have, 2 Dirac cones from layer 1 and layer 2 of graphene. The separation in momentum space between the Dirac points is proportional to the twist angle because it's already a small angle, okay? Now, this could be the situation that would occur in the electronic structure if these two graphene sheets, if electrons in one graphene sheet did not know that the other graphene sheet is nearby. But in fact, the two graphene sheets are only spaced by 3 angstroms. And so electrons are very much aware that the other graphene sheet exists and can, in particular, tunnel between the two graphene sheets. That tunneling leads to bonding anti-bonding states, okay? Similar to bonding anti-bonding states in a hydrogen molecule, but this is now a giant graphene molecule, okay? And that leads to this, bond repulsion here at that crossing point, yeah? This is due to the interlayer tunneling or interlayer interaction. And now this is the situation when this interlayer tunneling is small compared to the energy of that crossing point, which is Fermi velocity times k theta, okay? However, as we decrease the twist angle, these two Dirac points get closer and closer in energy, and this band, which gets pushed down in energy, gets pushed down to lower and lower energy until it touches 0, okay? When that thing happens, we say that the flat band condition has been realized, and that flat band condition is reached at an angle which depends on this interlayer tunneling, and it's called the magic angle, okay? And happens to be 1.1 degrees for graphene on top of graphene, yeah? So this, this magic angle term was coined by Bistritzer and McDonald. There was earlier theoretical work also pointing to the existence of these flat bands by Suarez Morel and collaborators. And there was also even earlier experimental work by the group of Eva and Dre, okay, where they looked at, a feature, by looking with the scanning tunneling microscope, they look at a feature in the density of states here, a Van Hoff singularity that occurs in this region. And they were able to see that those Van Hoff singularities go to 0 energy when you reach, an angle very similar to this one. Okay, so there was already very interesting single particle physics work, both experimental and theoretical, about a decade ago. So, okay, so what I showed you before was a cartoon. This is an actual calculation of energy versus momentum for this flat bands in momentum space. Okay, this is a single particle calculation. Now, flat bands in momentum space, if you want to think now, if I put electrons in these flat bands, where will they be? In real space, you have to do a Fourier transform, okay, to go from momentum space to real space. And flat in momentum space means highly localized in real space, okay? So if you look at where do the electrons like to go when you put them in these flat bands, they like to localize in regions where locally all of the carbon atoms in one layer are on top of the carbon atoms in the other layer, okay? We call these regions regions of AA stacking. And these regions where electrons like to be are separated by regions where, due to the small twist angle, the registry comes out of, the atoms come out of registry, and those regions are of AB and BA stacking, where only some of the atoms are on top of the other, and the others are on top of hexagons, okay? So from the top, magic angle bilayer graphene looks like this schematically. There are these regions of AA stacking where the electrons like to be, and these are separated by regions of AB and BA stacking, okay? In a slightly more realistic view, what you have is this. Okay? You have these regions of AA stacking where the electrons like to be. These are separated by about 13 nanometers. Yeah? And then the regions of AB and BA stacking and domain walls, where the electrons do not like to be. This forms sort of the equivalent of our triangular Fermi-Hubbard, this is the equivalent of a triangular Fermi-Hubbard lattice in cold atoms, except that I put triangular in quotes because this, in reality, this is a honeycomb pattern, okay, because the AB and BA regions are not equivalent. And also this lattice has interesting topological properties that I'm sure later today, I'll mention something about it, but probably later today, Andre or Oscar will mention more about. And that makes it impossible to just do a direct mapping between this and a traditional Fermi-Hubbard lattice, okay? Okay, so now let's start, I'm gonna start showing you some data. So before, let me show you what our device geometry is. So we make our magic angle twisted bilayer graphene devices. We encapsulate them by hexagonal boron Nitride, which is a very interesting dielectric material which keeps the magic angle graphene very pristine. And then we contact them with source and drain electrodes so that we can apply a voltage and pass a current. And then we have a nearby metallic plate. This forms a parallel plate capacitor with a magic angle graphene. And by applying a voltage to this metallic plate, we can change the charge density.
There is a question, Pablo.
Okay.
Chat. What is the typical localization length in real space?
So that's 13 nanometers, as I said here. This is the distance between this object, okay? It's 13 nanometers, okay? In reality, I mean, the wave functions for the electrons in the flat bands, okay? This is something that is a subject of debate, and they have a complicated shape and so on, okay? But let's say, center to center, okay, of a complicated distribution is 13 nanometers. Okay, so this is our device geometry. We have a field effect transistor geometry, so we can pass a current and modify the charge density in the channel by applying a gate voltage, okay? So now, as a reminder, if you have just monolayer graphene, regular graphene, okay, and you measure the conductivity as a function of density, okay, which you can, again, change electrostatically, you have the following situation. If you have lots of holes in your system, your Fermi energy is deep under the Dirac point, you have lots of holes, which happens large densities, negative densities, then you have lots of holes, so you conduct very well. If you tune your Fermi energy deep into the conduction band, you have lots of electrons, and hence you also conduct very well. If your Fermi energy is at charge neutrality, you have very few carriers and you conduct very poorly. So the conductivity of graphene versus gate voltage or versus charge density has this characteristic V-shaped behavior, okay? That's for regular graphene.
Another question.
Yep.
In bilayer graphene twisted, the properties are the same for both valleys. And
So in twisted bilayer graphene, let me see if I can go back to here. Okay, so you have a valley K and a valley K prime from one layer of graphene. You have a valley K and a valley K prime from the other layer of graphene. Okay, so the situation that I'm showing here, for example, is this is one valley from one layer and the other valley from the other layer. You have, of course, the other two valleys, from either of the layers. Okay, and the fact that these two valleys, this is something again that I believe Andre will discuss in more detail, but the fact that these two valleys have the same chirality is what endows the twisted bilayer graphene with special topological bands. Okay, and this is something that will be discussed later. Okay.
And there is another one. For a particular angle, is there a modulation in the interaction between layers?
So yes, so when you twist, in general, you have to think when you create a structure, okay, by twisting it, there's going to be points where the electrons have it easier to tunnel between the two layers and points where it is harder to tunnel between the layers. The initial models, okay, this Bistis and McDonald model initially assumed that this tunneling was, the same between, different sites. Now we know that that tunneling is not the same, okay, between and everywhere in space. Okay, there is a ratio of that tunneling, okay, which is about 0.8 between different sites, which controls the electronic structure, and it has to do also with relaxation of the lattice, and it controls, and it makes the electronic structure a little bit different from what it was initially thought. Okay, in particular, it opens, it isolates the flat bands from the more remote bands. Okay, so there is indeed some local structure, and again, these are approximations, but that approximation already, where you take into account that difference, seems to be in good agreement with the experiment. Okay, but of course, the tunneling is locally. Tunneling element varies locally in the Moore pattern.
That's it.
Okay, good. So the conductivity of regular graphene versus density is V-shaped. Let's look what happens when you go to magic angle graphene. Okay, so these are data of the conductance, okay, versus charge density, okay, for magic angle graphene. And as you can see, it's not V-shaped. It has, lots of ups and downs. Okay, so let's go through this a little bit. So these are the electronic structure here. Okay, so first thing is you have a region here, okay, which corresponds to adding 4 holes per more unit cell to your system, starting from charge neutrality from 0, okay, which corresponds to setting your chemical potential here in the middle of this band insulator, of this band gap between the flat bands and the next remote bands, okay, because in these flat bands you can put up to 8 electrons per more unit cell. So from charge neutrality, you can add 4 electrons per more unit cell or 4 holes per more unit cell. You remove 4 electrons per more unit cell, in total 8 electrons per more unit cell. Okay? By adding 4 holes, your chemical potential is here, and you're in the middle of a single particle insulator, and therefore your conductance is 0, because your chemical potential is in the middle of an insulator. Similarly, if you change electrostatically your chemical potential to the middle of this other band gap, by adding 4 electrons per more unit cell, or 8 electrons in total from here to here, okay, then you are also in a single particle insulator state. Okay, now those are, these gaps, this insulator behavior, these are modified by interactions, but the basic origin is trivial. Okay, it's a single particle gaps. What we saw, which was quite interesting, is that if you put now your chemical potential here, in the middle of the flat bands, by adding 2 holes per more unit cell, or here in the middle of the conduction band here, by adding 2 electrons per more unit cell, the chemical potential is in the middle of a band. So the system should be metallic, it should be a good metal. However, you have, insulating behavior at 2 holes and at 2 electrons per more unit cell. Okay, so that insulating behavior is not expected in single particle physics, and it is a correlated insulator state. Yeah? By the way, near charge neutrality, the system sort of behaves similar to graphene in that it has this V-shaped behavior of the conductivity versus gate voltage or versus charge density. Now, this type of behavior, where you have this correlated insulator behavior at 2 electrons and 2 holes per more unit cell, occurs only in a relatively narrow angular range around 1.1 degrees. Okay, so in our original paper we explored 4 devices, but now we have many dozens of devices, and we know roughly the distribution. This type of behavior occurs between 1 and 1.2 degrees. Maybe 0.95, 1.25 degrees. Okay, so in a relatively narrow angular range where these flat bands occur. Now, let's look at superconductivity. Okay, so these are the same data as before. This was taken at 0.3 Kelvin, and we were doing temperature dependence, about this data. And initially, we were looking at this correlated insulator states for electrons, and we saw that as we did temperature dependence, the colder the system became, the least it conducted. That's what you expect from an insulator. So that was consistent with the insulator behavior. And then we were looking at the region around 2 holes per more unit cell. Here again, from 1.7 Kelvin, if we cool down, the conductance goes down. That's what an insulator does, and that was okay. But then we noticed that right next to it, the colder it went, the more the system conducted. Okay, so that conductance enhancement, we were a little bit curious, that's a bit strange. Let's see how well this thing wants to conduct. Okay, it turns out this data, we were taking them in a 2-terminal geometry. We're making devices which were in a 2-terminal geometry, and in a 2-terminal geometry, this is a good geometry to measure the resistivity or the conductivity of systems that you expect to become insulators, because for an insulator, if the resistance is infinite, it doesn't matter if you add a series resistance by having contacts attached to your insulator. However, if you want to see if something is a very good conductor, you don't want to have a parasitic series resistance. Okay, then you have to make devices in a geometry known as 4-terminal geometry. And that's what we did. We made devices in the shape of a whole bar so that we can pass a current and measure the voltage drop within the device without any series resistance, and look really how well the system wants to conduct. Okay, and then so these are the new device that we made. 1.16 degrees rotation angle. This is we first measured it in a 2-terminal geometry because it's simpler. So this is that's why it's called. This is G2. Okay, the conductance in a 2-terminal geometry, and these are data at a finite perpendicular magnetic field. You can see this shape near charge neutrality. We have insulated states at 4 electrons and at 4 holes per more unit cell. And then you see that near 2 holes and 2 electrons per more unit cell, there is a dip here in conductance. Okay. There are also things, by the way, happening at 3 electrons and 3 holes per more unit cell. There are many things which I'm not telling you yet about, okay, but which are interesting also. And then it would, yep.
Maybe, sorry for interrupting. There are a couple of questions. I think we're going to try to accumulate questions in bunches of 2 or 3, and so that we don't interrupt you so much. So the first is Nicholas is asking: are the bands you showed in die binding calculations with a large supercell of carbon atoms, or is it in the basis of these Moiré sites?
So there are many calculations. The Moiré unit cell. Okay, because it's 10 nanometers, so you can imagine, right? It's 100 by 100 in terms of atoms. So it has about of the order of 10,000 atoms. Okay, so there are no calculations, that can do those 10,000 atoms, exactly, Plus there are several orbitals, so it's even more actually in terms of orbitals. Okay, so people do various types of approximations. Okay, in fact, there is an even earlier thing, which is not all angles are commensurate. Okay, so in general, for a generic twist angle, you don't even have a commensurate, a true periodic lattice. Okay, but it turns out for small twist angles, you can get rid of a lot of that complexity by taking, simplified models. Okay, in particular, the one that is, was most famous was the Bistritzer-McDonald model, okay, where is a continuum model, where you treat all of the things. Turns out for small angles, you can average over a lot of things. Commensurate, incommensurate, it doesn't matter too much, okay? So what people started to do after the Hexagonal model is people started to introduce different types of refinements. For example, relaxation of the lattice, okay? The fact that you start to take into account that the tunneling, depends on where you're in the Moray sublattice, etc., on the Moray lattice, etc. Okay, so that people started to introduce more and more refinement.
Okay, the second question is by Rafael. I think it's regarding your previous slide. Why does the G versus change? Why does the G versus charge density plot look not symmetric around 0, and the energy band, the band structure is symmetric around 0?
So
yeah, why? And then that's there's a second question. Why the enhancement only happens at the whole region? Yeah.
Okay. So first of all, the electronic structure is not symmetric around 0. Okay. It looks sometimes symmetric depending on which calculation one looks at, because in the most simple calculations, it is symmetric. But once you start including your next neighbor hopping terms, etc., the electronic structure is not symmetric. Similar to graphene's electronic structure is not symmetric. If you look at graphene at high energies, the electronic structure is asymmetric. When you make a Moray pattern, all that high energy asymmetry falls down to lower energies. Okay. Now, having said that, we do not know if the asymmetry between overall electrons and overall holes from charge neutrality is just due to single particle effects, or there are extra effects, okay? Because the asymmetry is quite pronounced. Now, this conductance enhancement, which is going to become superconductivity, initially in our first samples, we saw it only around 2 holes per more unit cell, okay? Because that's the strongest superconducting dome typically. Later on, we and others have seen it also around 2 electrons per more unit cell, okay? But still is asymmetric. Okay, so here are these conductance measurements versus charge density with the features that I mentioned. And then if we remove the magnetic field, we see that around 2 holes per more unit cell, a lot of stuff happens, okay? So we change then to our 4-terminal geometry, and we measure the resistivity versus temperature. And we saw these are data for 2 devices. By now we have dozens and dozens of these devices. And the resistivity versus temperature exhibits this precipitous drop, to 0, okay, below a certain temperature. And that means magic angle twisted bilayer graphene superconduct, okay? So not only it superconducts, okay? Well, by the way, let me show you also the voltage versus current characteristics, showing this, sharp abrupt switch, to resistive state, but 0 voltage dissipation, okay, at low temperatures. Okay? Now, not only it superconducts, because we can tune our charge density electrically by varying the gate voltage. Magic angle graphene is an electrically tunable superconductor, okay? So this red region is the region of 2 holes per more unit cell with this correlated insulator state. And then if you add extra holes, you have a big superconducting dome. If you add electrons with respect to these 2 holes per more unit cell, or if you remove holes if you want, then you have another superconducting dome, okay? So now this phase diagram, when my students show it to me, it immediately reminded me of this, hundreds of times that I've seen this other phase diagram. This is the phase diagram of the high temperature Cooper superconductors, where at 0 doping, meaning 1 electron per unit cell, there is a mod insulator state. And then let me change this axis so that hole doping, electron doping is the same as for us, okay? So if you dope with holes, you have a large superconducting dome. If you dope with electrons, you have a small superconducting dome, okay? Now, of course, the difference between, there are many differences between these 2 phase diagrams, but the most, one of the most important ones is the fact that this is a theoretical phase diagram. In order to populate this phase diagram with actual experimental points, you have to grow hundreds of crystals, so that they give you, with different chemical impurities and different material classes, so that they give you points in this phase diagram. This is all done in a single device, with a single disordered realization without chemical impurities. And it takes me, a few seconds to go from here to here, okay? So that, attracted a lot of attention. Now, I should mention that there are, as you can see, many similarities between these phase diagrams, but there are also many differences, okay? It's not yet clear to what extent the similarities between Heidelberg-Jacobi superconductors and magic graphene are, to what extent the similarity stems. So I should mention also that more often than not, what we see is a very asymmetric situation where the superconducting dome for electrons is very small compared to the one for holes, okay? All of the devices that exhibit very high temperature, in this case, high temperature, I mean, of order 1.7 Kelvin in this one, but later on 2-3 Kelvin, the domes are very asymmetric. Now, so, okay, I just showed you that, the critical temperature is of the order of 1 Kelvin, okay? Maybe 3 Kelvin in our best devices. Now, how strong a superconductor is magic angle twisted bilayer graphene, okay? Turns out the strength of a superconductor from a physics point of view is not characterized by how high the critical temperature is. Okay? That's very important, if nothing else, for applications. But the strength of a superconductor is characterized by how large the critical temperature is compared to how large the Fermi temperature is. Okay? So this is something which is typically shown in it's known as Uemura plot. So here you have critical temperature in log scale versus Fermi temperature in log scale, okay? And conventional superconductors are typically in this region, okay? They have relatively modest critical temperatures and very high Fermi temperatures, okay? If you take, for example, aluminum, it has a critical temperature of 1 Kelvin, similar, same order of magnitude as magic angle graphene, but a Fermi temperature of over 100,000 Kelvin. So given the gigantic density of electrons that aluminum has, it superconducts modestly, okay? Now, as you go more diagonally towards this purple band, your superconductivity becomes more and more exotic. And in fact, in this purple band, you find all of the unconventional, pretty much all of the unconventional superconductors. You have here the cuprates, the iron pnictides, organics, the heavy fermions, okay? They're all kind of in this purple band. Yeah? I've included also here some data points from ultra cold atom systems, both axes multiplied by 100 million, so that they appear here. But in terms of coupling strength, they're the strongest coupled systems that we have. Okay. Now, where is magic angle twisted bilayer graphene? It's here. Okay. It's one of the strongest coupled superconductors that we have. Okay. It has a TC of the order of 1 and 2 Kelvin for this data point from our original paper, but a Fermi temperature of 20 Kelvin or so, a little bit less. Okay, so given how few electrons magic angle graphene has, because remember, it has electrons which are a fraction of an electron per Moire unit cell, but it's a huge cell. So the density of electrons in magic angle graphene is the lowest of any superconductor. Okay, of any superconductor in 2 dimensions by over an order of magnitude. Okay, so given how few electrons it has, it superconducts very strongly. Okay, so we announced this discovery at the APS March meeting in 2018. Okay, and then immediately a lot of people were asking, what is the origin of these correlated insulators and what is the superconducting order parameter, and this is just a small fraction of the papers that appear within a few weeks of us posting our results. There were all kinds of theoretical proposals. We've included all letters of the alphabet for the superconducting order parameter, S, P, D, S plus P, S plus P plus D, P plus IP, you name it, okay? So I don't wanna say anything about, we don't know yet which one it is, okay? It's still active, very active topic of research, experimentally and theoretically, to determine these things. Okay. Now, let me tell you a little bit about some of the experimental developments since the paper was officially published in April 2018. Adolfo, any questions?
Yeah, maybe I can stop you here. I think you briefly mentioned, but I think there's a question on can we understand the dip in conductance versus density at n equals 0 from single particle effects? I think, I think it's
for electrons in graphene. Okay.
Yeah.
So at charge neutrality, you have a dip in
Yeah.
conductance in the same way that you have in graphene.
Okay, so I guess the answer is
okay.
yes. And I have a question actually. In this plot you showed with TC and TF, I think all of them are crystalline or like not very disordered superconductors, but you also have like very strongly disordered superconductors. How do people characterize the strength of superconductivity there, and is there a way of plotting all together? Or?
So, you know, aluminum, you know, can be crystalline or can be very, you know, amorphous, you know, when you grow it. Many of these materials has huge levels of chemical impurities and disorder. You know, they're not that crystalline actually. Many of the materials, you know, that are shown in this plot. So you can still measure the critical temperature, and you still can get an estimate either of the Fermi temperature or the, you know, the density of carriers in the system. You know, so you can still put them somewhere here, you know, with appropriate error bars if you want.
Yeah, I didn't see the upper axis. Yeah. Okay, great. Thanks.
So, okay. So our paper was published our papers, you know, they were published in April 2018. And then what has happened since then? Okay, so let me tell you some of the experimental developments since then. You know, the first thing is that we have reproduced our own results many times, okay? Believe it or not, that doesn't always happen, so it's good when it happens. So, you know, since then we have accumulated many more data. In fact, we're starting to have, you know, optimal doping TCs versus twist angle, you know, a new type of superconducting dome, TC versus twist angle, a new parameter in solid state physics, and other people too. Now, many groups have independently reproduced, you know, even better than you reproducing your results is when others do it, only then it becomes true science. So many groups have independently reproduced our results and even extended them to other systems, okay? So the first two groups to reproduce our results were a collaboration between a group of Corey Dean at Columbia and Andrea Young at UC Santa Barbara, where they not only reproduced our results, but extended them very interestingly to what happens when you apply pressure to twisted bilayer graphene. The other group, you know, the next group to reproduce our results was the group of Dmitry Efetov, who they were able to see in one device also additional superconducting domes, you know. Then, you know, robust superconductivity has been now reproduced and extended by many groups, you know, about a dozen or so, and more are, you know, joining, you know, every other month. Now, the system exhibits many other characteristics of correlated materials. For example, linear resistivity behavior, which is typical of strange metals, you know, and Planckian physics. I will talk about this in tomorrow's lecture. Also, anisotropies in the critical, you know, in the parallel critical field and in the critical current versus parallel magnetic field, indicating that there is nematicity in the superconducting state, also in the normal state. And I will also talk about this tomorrow. Okay. We have also other twisted, you know, systems which exhibit correlations. The second one to be discovered was magic angle twisted bilayer graphene. So it's 4 layers of graphene, 2 of them with 0 angle, 2 of them with 0 angle, and then twisted at the magic angle between them. Okay, we call it magic, magic angle bye-bye. Okay, so I will not mention this, okay, but you can look at the references in my group's website or in others. It's very interestingly, people have started to apply various scanning probe microscopy methods to these systems. Okay, I will mention a little bit about one of them, scanning single electron transistor studies, tomorrow or on Wednesday or on Thursday. But also STM, and people are looking now locally at the structure of the system, also scanning near field optical microscopy, scanning nanosquid, all kinds of scanning techniques, and they are providing very interesting information. And then, perhaps one of the most interesting developments was the observation of ferromagnetism anomalous Hall effect and quantum anomalous Hall effect in the system, which means that topology plays a key role in this type of more heterostructures. Okay, in fact, Its correlated more heterostructures has meant the merging of several modern condensed matter communities. Okay, on one hand, the 2D van der Waals materials and heterostructures community, people that work on graphene, like myself. Then on the other hand, the people that work more on traditional strongly correlated materials, such as cuprate, nitrides, etc. And then the people that work on topological condensed matter physics, quantum and fractional quantum Hall effect, topological insulators, etc. All three of these come together in these correlated Moiré heterostructures or Moiré quantum matter. Okay, and one of my biggest pleasures is to now interact a lot more with people in these other communities that I didn't talk to so frequently. So together with my collaborators at MIT, we already predicted, the existence of nearly flat Chern bands in various types of Moiré superlattices. Okay, and there was, related theory work on the topology of these systems. And then shortly afterwards, the group of David Goldhaber-Gordon, measured a very large anomalous Hall effect on magic angle bilayer graphene, which was aligned, to hexagonal boron nitride, to the hexagonal boron nitride underlying substrate. And then a few months later, the group of Andrea Young reported the quantized anomalous Hall effect, okay, in the system. Okay, so very interesting developments. Then the other thing that happened is that, for a while, the community was searching for a second Moiré superconductor. Magic angle bilayer is not a superconductor, and several others, there were doubts. So finally, earlier this year, we discovered a second robust Moiré superconductor, magic angle twisted tri-layer graphene. Okay, and there will be other surprises to come soon. But this system, magic angle twisted tri-layer graphene, a few months ago, both my group and the group of Philip Kim at Harvard, okay, we published back-to-back papers in Nature and Science with the discovery of this new system, magic angle twisted tri-layer graphene. Turns out to be an even more interesting system than magic angle bilayer graphene, okay? And this will be the subject of my third talk, my third lecture on Thursday, okay? A very interesting system. Now, you can see that, with Moiré quantum matter, we have pretty much, discovered, or realized all of the traditional, phases of condensed matter physics, or most of them, okay, from correlated insulators, superconductivity, various topological phases, magnetism, nematicity, okay, this in graphene-based and also transition method like chalcogenides and related Moiré systems. Now, one which was until a few months ago absent was, ferroelectricity, okay, but then, a few months ago, three groups independently, we reported a new type of ferroelectricity called Moiré ferroelectricity in a new type of Moiré heterostructure, twisted bilayer boron nitride. Okay, so let me show you in the last 5-10 minutes. Let me tell you about this. So, there are a few two-dimensional ferroelectric materials. I think almost all of them are in this slide. Okay, just very few. Maybe half a dozen, something like that. Okay, now all of these materials are ferroelectric 2D materials which are obtained by exfoliating bulk polar materials. Okay, so the bulk material was already polar. You exfoliate it down to a monolayer, which turns out to be a ferroelectric material, or down to a few layers. Now, I'm talking about something here different. Okay, so take bulk bilayer hexagonal boron nitride. Okay, so in hexagonal boron nitride, the natural stacking is called AA prime. Okay, that means, so first of all, hexagonal boron nitride, is a honeycomb lattice similar to graphene, except that now instead of having the two sublattices have carbon atoms, you have nitrogen and boron atoms in the A and B sublattices. Okay, now the natural stacking is AA prime, meaning a boron atom has on top a nitrogen atom has on top a boron atom, and they're exactly alike, okay, like this. So natural stacking for bilayer bulk boron nitride has HBN layer number 2 rotated by 180 degrees on top of layer 1, okay? As you can see, the second layer is rotated 180 degrees with respect to the bottom layer, and they're exactly aligned in terms of the hexagons. However, if we do parallel stacking of bilayer hexagonal boron nitride, then we have a non-centrosymmetric system. This structure is centrosymmetric, okay? However, this structure, parallel stacking bilayer HBN, is non-centrosymmetric, okay? So you can do the following thing. You can take a monolayer of hexagonal boron nitride. Let me put guides to the eyes to the boron and nitrogen atom locations. And now I'm going to break it and stack it parallel to itself with 0 degrees without rotating it 180 degrees. If I do that, now all of the nitrogen atoms are on top of nitrogen atoms, all of the boron atoms are on top of boron atoms. This is a non-centrosymmetric structure, and it's also a very uncomfortable structure because these atoms are repelling each other essentially. Okay, so what the system decides to do is the system shifts to a more energetically favorable configuration, which is AB stacked Bn, where the boron sits on top of the nitrogen, or alternatively, BA stacked Bn, where the nitrogen sits on top of the boron. Okay, and it turns out these two configurations, AB and BA, they have permanent electric dipole moments, which are opposite. Okay, so if you can switch between these two configurations, you have a ferroelectric, a switchable ferroelectric material. Okay, so this is exactly what we did. We took a monolayer of hexagonal boron nitride, we broke it, okay? We stacked it parallel to itself. So this is parallel stack bilayer boron nitride. And then what we did is we deposited on top graphene, which is a conductor. And the graphene is going to become a ferroelectric, together with the parallel stack boron nitride, is going to become a ferroelectric field effect transistor. Okay? Where depending on the polarization of your ferroelectric, you are going to have one type or the other charge carriers in the graphene, and therefore you're going to have a change in the resistance. Okay, so indeed, if you do this and measure the resistivity of graphene versus applied gate voltage, in this case, divided by the distance, so it's an electric field. Okay. Remember that I told you that the conductance of graphene has this V shape. The resistance, which is one of the conductance, has a peak shape, okay? And if we sweep our gate voltage in one direction, we have this peak. If we now sweep back, we have also a peak, but it's shifted with respect to this one, okay, because of the hysteresis, okay? So we have ferroelectricity and hysteretic behavior. You can do this in a more controlled fashion by looking exactly at both the back gate and the top gate sweeps, because we have dual gate geometry. And you can see in this map, we have a diagonal. When you have ferroelectric switching, you switch here to the side. If you now sweep backwards, you have this diagonal which continues on this state, and then it switches abruptly to this state, okay? In fact, sometimes we can briefly catch a ferroelectric domain as this switching is taking place, and we can see two peaks, corresponding to both domains. Okay. Now this is for parallel stacking. What we can do also is we can make a small angle of rotation. Okay, small twist. So small angle twisted bilayer hexagonal boron nitride. Then we have AA, BA, and AB regions similar to magic angle graphene, but now these BA and AB regions correspond to different ferroelectric domains, okay? And now when we apply an electric field in one direction, we will be increasing the size of one type of domain and decreasing the other type. If we apply the opposite electric field, we will be increasing the size of the other domain, okay? So if we do that and we fabricate graphene ferroelectric field effect transistors on small angle twisted bilayer boron nitride, this case 0.6 degree rotation angle, what we can see is that we have now the presence of these two resistive states, okay, because of the coexistence of the domains, okay? So you can see this is different from the abrupt switch when you have 0 degrees, when you have parallel stacking, okay? Now, can we visualize directly these ferroelectric domains? Indeed, we can do that. We can do that by using a technique called vertical piezoelectric force microscopy, which tells you directly, if you have an electrode dipole moment out of plane. And as you can see here, both in the phase and the amplitude image, this is a vertical piezoelectric force microscopy, and you can see the beautiful, moire pattern, the AB and BA domains with opposite electric dipole moment. Okay, similar images were obtained by other groups. Now, this ferroelectricity is robust. It works even at room temperature. Okay, so it's a very robust effect. Here you have data, all the way from 10 Kelvin up to room temperature, and in fact, you can, and it lasts for very long, for as long as we waited. We waited up to a month, and it still was present there. Okay, so this means that this, who knows, this might be, useful for applications perhaps one day. So with this, I want to just remind you all that this field of Moiré quantum matter, correlated Moiré heterostructures is a very rich field where many different communities are coming together. We're at the beginning of this field. Okay, so for all of you who are students, this is a very interesting field to get into. It's one of the most active fields of condensed matter physics today. And I want to end my first lecture today by thanking my grad students, postdocs working on the project, collaborators. I hope that soon we can get all back to these types of events, and also thanking the funding agencies. And I want to thank you for your attention. I'm happy to take any more questions.
Thank you, Pablo. Thank you for this very, very nice talk and fantastic introduction. So I'm going to read you 3 questions that there are in the questions and answer chat. And I suggest the rest to write your questions on Slack, and we will read them tomorrow before the next talk of Pablo, because we are a bit tight in time. So, okay, Umesh, what are your views on different samples from different groups showing extra missing superconducting domes, insulating states, and the integer fillings? What can be the plausible reasons for these variances in the data?
Very good. So there are 2 things. Already at a very simple level, the electronic structure of magic angle bilayer graphene is extremely sensitive to the precise twist angle on increments which are of the order of 0.01 degrees. So it's not surprising that a sample which has a twist angle of 1.05 degrees could have different properties from a sample that has 1.15 degrees, 0.1 degree apart. Okay, it's extremely sensitive, the electronic structure, even at the single particle level, to the precise twist angles. In addition, different devices have different degree of disorder, twist angle disorder, which is a new type of disorder, this twist angle disorder. Okay, and this twist angle disorder, in particular, makes it sometimes harder to see the correlated insulated states, because in terms of the phase diagram, the correlated insulated state has a narrow density range over which it is seen. The superconducting domes have a much larger density range over which they are seen. So if you're going to average over disorder, the easiest to disappear is the correlated insulated state. Superconductivity is a bit more robust. That's why it's more frequent to see superconductivity than correlated insulated states if you are within the magic angle range. Okay, so those 2 are, I think, the most important factors: the precise twist angle and the degree of disorder.
Next question from Alexei Bondarev. Roughly, how is the parallel stacking achieved experimentally?
So the way we achieve it is we find, we exfoliate bulk hexagonal boron nitride, and we find pieces which are monolayers of hexagonal boron nitride. And then if you have a large piece of hexagonal boron nitride monolayer, then you can pick up with a polymer half of this piece, break it, and deposit it on top of the other half with 0 angle, okay? With 0 degrees angle, without rotating it 180 degrees, with 0 angle. That's why how you reach parallel stacking, okay? And there are slightly different techniques for tearing, for cutting, for how to do this process, but that's the basic thing. You take one monolayer, break it in 2, and stack it on top of each other. And because the 2 pieces came from the same piece, from the same crystal, they are aligned. That's how you guarantee a small angle between the 2 pieces.
Okay, and the last question from an anonymous attendee. Can you switch between the AIB, AB, or BA packing in the hexagonal boron nitride by means of an electric field?
Yes, that's precisely what we're doing in this data, okay? In this data, what we're doing here is we're going from BA stacking to AB stacking. So it's a sliding transition, okay, this ferroelectric switch.
Okay, then. Thank you very much, Pablo. And
thank you, everyone.
And see you tomorrow at the same time. And our next speaker is Jennifer Cano. Hi, Jen.
Hi, Maya. Hi, everyone. Can you hear me okay? Everything is good?
Yeah, at least I can.
Okay, great. So since we're starting, say 10 minutes late, maybe I'll just end 10 minutes late, something like that.
Yeah, sure.
Okay. Okay, great. So let's share my screen. Okay. So I will get started. So in this first lecture, I'll give an introduction to topological insulators. So this will more or less be the fundamentals going back to basics, and this will set the framework for my next two lectures. So the next lecture will be on topological crystalline insulators, and that will lead into topological quantum chemistry. And then on Friday, on the third lecture, we'll talk about topological semimetals. So, so this lecture is, I just want to cite this review article by Hassan and Kane at the bottom. If you're interested more in learning the fundamentals of topological insulators and superconductors, then I strongly recommend this article. So to start off with, in order to contrast a topological insulator, we first just need to mention what is an insulator, as everyone probably knows. So an insulator does not conduct electricity. So I showed here some examples of insulators, but from a band structure perspective, an insulator does not have any low energy excitations. And so in other words, there's a gap between the top of the valence band and the bottom of the conduction band. So not all insulators are the same. Of course, this is what we're going to try to do, motivate that there's different types of insulators, including topological insulators. But I wanted to first go back to maybe the most fundamental example of a topological phase, which is the quantum Hall effect. So I just said that an insulator should be something which does not have low energy excitations. And so now if we think about the quantum Hall effect, the quantum Hall effect describes 2D electrons in a strong magnetic field. And what happens is that the magnetic field quantizes the electron motion. And so we end up with this, these series of quantized energy levels. And since these energy levels are dapped, if the Fermi level, so these are Landau levels, these flat bands, and if the Fermi level is between two energy levels, then this fits our definition. There's no low energy excitations. In order to excite an electron, you need to make a jump of a non-zero amount. So this thing should be an insulator. And if we look at the data of the longitudinal magnetoresistance, we see that it is an insulator. On all of these plateaus, we see these regions where the resistance is zero. So that fits with our previous definition. But in addition to the longitudinal resistance, we have the Hall resistance, and this thing is manifestly not zero. And of course, the important feature here is that we can see not only is it non-zero, but the Hall resistance is appearing in at these quantized values, which are these steps here. And so these quantum Hall devices seem like they should be insulating because there's no low energy excitations, but actually they are conducting, and we see this from the Hall resistance. So this tells us that there's a different type of insulator, and it also provides our first example of a topological invariant. So a topological invariant is something which is not changed under small deformations. And so the usual example that people show is this coffee cup donut. Each one of these things has one hole in the structure, and this motivates the definition of a genus. So the genus is basically telling me for some object, how many holes are there in the structure, and I can smoothly deform one of these to the other. You've probably seen the animation, but the notion of a genus does not change under this deformation. Well, the Hall conductivity is a more physically relevant example of this. We see the Hall resistance here, and it's sitting on these quantized plateaus, and it stays quantized even though we change the magnetic field, because this x-axis is magnetic field, and it also stays quantized across many samples, which might have, say, different amounts of disorder. So the Hall conductivity is also serving as a topological invariant. It's an integer number. We see it's an integer here because we can map these steps and look where they lie. It's an integer number, and it doesn't change even when the system undergoes these small deformations. Now, we'd like to understand how the quantum Hall effect can conduct electricity, even though there's a gap to excitations. And so one way that we can understand this is if we plot the Landau level spectrum on a system with edges. And so the previous plot of Landau levels, which was just these flat lines, would be for an infinite system. But if we consider boundary conditions, and if we consider, say, hard wall boundary conditions, then these Landau levels must be consistent with the fact, or the energy levels must be consistent with the fact that electrons could not penetrate hard wall boundary conditions. And so what happens is that the Landau levels curve up at the edges of the system. And then, in fact, we see that at the edges, the system is gapless, even though in the bulk of the system, there's a gap. And so this is one way to understand how a quantum Hall system can be insulating in the bulk, but gapless at the edges. And we can also understand this from these cyclotron orbits. And so electrons in a magnetic field will move in little circles, but at the edges, these circles will be incomplete. And this creates some extra state along the edge of a quantum Hall system, which conducts electricity. And there's yet another way of visualizing this, which is in some insulating system, there'll be some extra, in the bulk, there'll be a conduction band and a valence band. But if we plot the system on an edge, or on a 2D system that has edges, then we'll see that there's this extra state that appears. And so in the bulk band structure, there'd be a gap to excitations from the valence band to the conduction band. But if we plot this on a finite system, there's an extra state which is gapless on the edge. And so I'm drawing these pictures here because later we'll come back to pictures like this, which are called like the surface band structure. So from the surface spectrum, we can understand how a quantum Hall system will conduct, even though it's gapped in the bulk. So this is actually an example of the bulk edge correspondence. This is a pretty fundamental property of topological phases of matter being gapped in the bulk, but having gapless edges. And this is made explicit early on, even before topological phases were in vogue, by this TKNN invariant, which is the initials of the authors in this old PRL from 1982, where they wrote down this expression. They explicitly computed the Hall conductivity, and they showed that actually we can understand the Hall conductivity from a bulk invariant. And so this expression, I'll get to this later, but this expression is in terms of the bulk eigenstates. That's what the U's are. And so the point here is that we're understanding the Hall conductivity from the surface current, but actually you can also compute the same invariant from the bulk itself. And so that's the fundamental attribute of this bulk edge correspondence. The gapless states are on the surface, but in order to predict whether or not there's surface states, we don't actually need to look at the surface. We can compute some feature of the bulk itself. And that's the fundamental nature of the bulk edge correspondence. So this, right now, if you haven't seen this before, this formula is looking a bit confusing. And so what I now want to do, keeping this quantum Hall effect in mind, is to back way up and do some more canonical examples in 1 dimension, and then build up to 2 dimensions, and then give some intuition for why the Hall conductivity might be quantized by using these earlier lower dimensional examples. So I think this expression here is kind of actually more like the end point of the talk. And now we'll back up and see how we can get quantized invariants. So the fundamental starting point that we need is first Bloch's theorem. And so I'm always going to be talking about topological phases in crystals, although there's a very interesting literature now about topological phases in non-crystalline systems. And so the fundamental attribute of crystals is that crystals have translation symmetry. And because of this, there's some translation operator that commutes with the Hamiltonian. And so the eigenstates of this periodic Hamiltonian can be simultaneously diagonalized with the translation operator. And Bloch's theorem tells us that we can write these eigenstates as a product of 2 terms. One is going to be some phase, and the other is the other part has the same periodicity as the crystal. So we call this the cell periodic part of the wave function. And all of these topological invariants are going to be computed in terms of the cell periodic part of the wave function. And so probably, as you know, each one of these wave functions which are eigenstates of translation, are labeled by a wave vector k, and the distinct wave vectors reside in the first Brillouin zone. So I'm drawing the first Brillouin zone here in 2 dimensions. Kx goes from minus pi to pi, ky goes from minus pi to pi, and we should equate pi and minus pi so that the square actually has the topology of a torus. And then in order to understand the properties of some material, we'll plot the eigenstates of these eigenvectors, and this gives us a band structure. And so this is just some schematic band structure, which I've drawn here, which is just energy eigenvalues as a function of this wave vector. The important point is that we need to have a notion of what it means for band structures to be topologically equivalent. So I already mentioned that a topological invariant is something which remains unchanged to smooth deformations. So what is a smooth deformation of a band structure? A smooth deformation of a band structure is moving the bands around, and a non-smooth deformation is when bands cross. And so if we start with, say, a band structure of some atomic insulator, so we assume that our atoms are very far apart from each other and the bands are completely flat, there's no hopping between atoms, then a smooth deformation is that we slowly introduce some hopping terms, and we would say that these structures are all topologically the same as each other. And what would not be topologically the same is if this band gap closed and 2 bands crossed and reopened, and that would be a topological phase transition in the band structure. So the important notion that we need to diagnose topological phases is the Zac phase. So the Zac phase is just the Berry phase around closed loops in the Brillouin zone. So you've probably seen Berry phase before in the context of varying some parameter in the Hamiltonian and seeing how the eigenstates change as you vary that parameter. Here, we're going to do the same thing, but that parameter is this wave vector k. So with that in mind, we can define the usual notions of Berry connection and Berry phase. So the Berry connection is just the overlap between one of these cell periodic parts of the wave function u and the derivative of u. So we usually write it in this way, and we usually call it u du. And then the Berry phase is just the integral of this Berry connection over some closed loop. And the fact that it's a closed loop is important because that's what makes the Berry phase path independent. If it wasn't a closed loop, then you could choose different paths with the same endpoints, and you'd get a different Berry phase. And this is also the reason why you might wonder, could we write down the same expression with the full block eigenstate instead of just the cell periodic part u? And the answer is not really. It wouldn't be well defined because the full wave function had an extra phase e to the I kr. So if we take the derivative of that with respect to k, we'll pull down a factor of r, and then integrating this thing will end up diverging because r is spanning the entirety of space. So it's actually very important that we use the cell periodic part of the block wave function to compute Berry phase and other topological invariants. Okay, but as you know, there's some ambiguity in the phase of a wave function. So for any wave function u of k, we can always add some phase to it. And this phase will also translate to an extra term in the Berry connection. And this extra term in the Berry connection will also translate to an extra term in the Berry phase. And so if we look at what this extra term in the Berry phase is, we see that it's an integral of a derivative of phi. And so this integral of a derivative, you might think since it's over a closed loop, it has to be 0, but actually it can be a multiple of 2 pi because over a closed loop, the phase is only defined mod 2 pi. So it doesn't need to come all the way back to itself. It can come back to itself mod 2 pi. And so this wave function phase ambiguity is why the Berry phase is only defined mod 2 pi. And this actually makes sense. This is why we call it a phase, because most phases are defined mod 2 pi. So this is important, but not that surprising. And finally, I should mention the Berry curvature. This thing is the Correlated, and this is actually gauge invariant because we see if we take if we plug this extra term into the Berry curvature, the curl of the gradient will disappear. And so Berry curvature is gauge invariant, but all these other quantities are gauge dependent. The Berry connection is gauge dependent, and the Berry phase is only defined mod 2 pi due to this gauge choice. So the special thing, one special thing is that in one dimension, the Berry phase gives a polarization. And so we can just the normal polarization that you're familiar with. And so the way to understand this, well, first off, let me simplify this expression for Berry phase to one dimension. In this case, there's only one K variable, and the closed loop that we're integrating around is just the entire Brillouin zone. So 0 and 2 pi are identified. So the Brillouin zone is just a circle. And so the Berry phase is integrated over that circle. And so we can heuristically understand why this Berry phase would give us polarization, because we can make this canonical substitution that I partial k can be replaced by x, just like I partial x can be replaced by k. And so with that substitution, we can kind of see that this integral is really the expectation value of the position operator x. And that's exactly what the polarization is. The polarization in a continuous system would be integrating over all degrees of freedom, and then computing the charge at each of those points. And so the polarization has this extra factor of E out front for charge, and then it's just integrating over all the degrees of freedom and taking the expectation value of position at all those points. So the Berry phase in one dimension gives us the polarization along that dimension, along that direction. And so now you might think that there's some ambiguity because I just said that the Berry phase is only defined mod 2 pi, but it seems like the polarization is something that should be well defined. And the resolution of this is that the polarization for an infinite crystal is only defined mod E. It's actually not well defined. Well, it is well defined, but only up to the electron charge. And the reason for this is that for an infinite system, it's not clear. There's multiple choices of unit cell that you can choose. And so, for example, this is a very simplistic system that I'm drawing here, which would just be an infinite line of positive and negative charges. We could choose a unit cell like this that has a negative charge to the left and positive to the right, or we could choose the opposite unit cell. And if you compute the polarization for either of these choices of unit cell, you'll see that one gives you a polarization of E over 2 and the other minus E over 2. So the polarization will differ mod E depending on which unit cell that you choose. And this is exactly consistent with our Berry phase being defined only mod 2 pi. So there's no inconsistency here. And so we can firmly say Berry phase in 1D gives us polarization. And then we can also, so the polarization of an infinite system is only defined mod E, but actually differences in polarization are well defined, because if we compare, so suppose we have two different systems, but we can tune from one to the other by some parameter in the Hamiltonian, then we can write down the difference in polarization. And if we go through these steps, plugging in the polarization formula and taking this derivative, we'll see that ultimately through a little bit of algebra, difference in polarization can be written as the curl of A, and this quantity is gauge invariant. So, so the main point is that we can understand differences in polarizations in a concrete way, even though the polarization itself for an infinite system is only defined mod E. And this connection between Berry phase and polarization is now known as modern theory of polarization, and these are some of the early papers introducing this concept. So now I want to give a little example, which is kind of the canonical example of a 1D topological phase. Later, we can come back to the question of whether we should call this thing topological or not, but it's certainly called topological in the literature. So this is called the Heger model, or usually known as the SSH model after these authors. So the model is as follows. This model is meant to describe polyacetylene, which is a chain of carbon atoms. Question?
Yes, I have a question. I think it's good to do it now. Is the Berry phase only different to 0 only in polar systems?
Is it only different from 0 in polar systems? Right, exactly. So yeah, that's exactly it. So the Berry phase gives the polarization. And so if you have some system which does not have a polarization, which would mean that the electron charge is located exactly on the atom charge, then this thing would have a Berry phase of 0. And so one way that we can understand how to get a non-zero polarization is that if your electron charge is not sitting exactly on your atoms, but is moved over some amount. That thing will give you a polarization, and that will give you a non-zero Berry phase.
Okay, and there is another question. In a strongly correlated system whose quasi-particles have a fractional charge, is the polarization only defined mod E2?
Okay. This is an interesting question on many levels. So I should say that right now I'm only talking about band structures. So the theory that I'm describing does not really apply to strongly correlated systems. However, due to this, the statement which holds all the time in all situations is that the polarization, it's really a polarization density, but because the full polarization would be infinite for an infinite crystal. Anytime you have an infinite system, there's ambiguity in this notion of what the polarization per unit cell is because of this choice. And so if you work this out for yourself, you're familiar with the fact that for a charge neutral system, the polarization does not depend on the choice of origin. Okay, fine. But now you can also, if you kind of repeat the same calculations for some infinite crystal, if you compute polarization density, you'll see that depending on density means polarization per unit cell, and you need to define your unit cell. And it's not always clear what the unit cell should be. And these different choices of unit cell, you can see that if you shift by a full lattice vector, one of the atoms in the unit cell, you'll change your polarization mod E. So in strongly correlated or any system, polarization density of an infinite crystal is only defined mod E.
Okay, thanks. That's all.
Yeah, great. Yeah, please feel free to ask questions anytime. Okay, so I was going to give this example of the Sushi for Heger model. And so what this model is, these blue dots are meant to be carbon atoms. And the point is that, let's see, there's all these hydrogen carbon bonds. And because of the number of electrons floating around, these carbon atoms could make single bonds or double bonds. And so if we wanted to write down a Hamiltonian for this system, we would write down some hopping amplitude to get from, I'll call these A and B sites. So to get between neighbors, there's some hopping. But if you have a single bond or a double bond, it'll make the atoms a little bit closer to each other or a little bit further from each other. And so this hopping should not be the same between all the atoms. Between some of them, it'll be a little bit weaker, and some of them it will be a little stronger. So in type binding language, we can write this down as some Hamiltonian, which has a hopping from A to B, and then a hopping from B to A. And these things will have a magnitude average of T, that's just the hopping parameter, but plus or minus this small parameter delta. And depending on whether delta is positive or negative, we interpret that as either having single bond, double bond, or double bond, single bond. So there's these two different possible configurations. And so we can plot the energy spectrum for both of these cases. And what we see is that the energy spectrum has a gap, and that gap is proportional to the size of delta. Now, in these two different systems, the electron charge in the ground state is localized more strongly on the double bonds. And so if we think of just one free electron sitting in the valence band, if we compare these two structures, in one case, the electron density will be more localized, say on this double bond. In the other case, it will be more localized here. So there's a shift of electron density by half a unit cell. The full unit cell has two atoms. And so we can see that if we change the sign of delta, we'll change the polarization because we're changing where the electrons are located. We'll change the polarization by half a unit cell, so E/2. And due to this relationship between polarization and Berry phase, there is a shift in the Berry phase between when we change this sign of delta between these two different phases, there's a shift in the Berry phase. The Berry phase shifts by pi. And so this is actually, with the appropriate symmetry, the Berry phase is actually fixed to either be 0 or pi. You need to have inversion symmetry to do this. And so this is actually the simplest example of a topological transition. These are both insulating phases. And as we, if we change delta from positive to negative, we'll have to close the band gap and reopen it to get from one phase to the other. And when we do that, the Berry phase will jump from pi to 0. So this thing constitutes a topological transition where the topological invariant is given by the Berry phase. And physically, we can understand this Berry phase. The difference between the two phases is that the polarization is, the electrons are basically moving by half a unit cell. Just to say, there's an alternative explanation of this Berry phase. All the physics is the same, but we can understand this as a winding number. So I'll just explain it lightning fast. We can write this Hamiltonian on a basis of Pauli matrices, which act on the A or B atom in the unit cell. And like I said, we need some type of symmetry here, say inversion symmetry. With the right symmetry, this Hamiltonian only has sigma x and sigma y matrices. And so you can define some winding number, which is if you take the coefficient of sigma x and sigma y, how does that coefficient change as k winds around from 0 to 2 pi? And the winding number will either be 0 or 1, which corresponds to this Berry phase of 0 or pi. But the other thing I want to say about this model, so this is a 1D topological phase transition. And we said earlier that one of the defining attributes of a topological phase should be a bulk edge correspondence. So how do we see that here? Consider a boundary between these two different phases. So one of these is going from single, double bond, and then it switches double, single, double, single. So there'll be some boundary here. And what happens is that at this boundary, there's an accumulation of charge. And so we can see that there should be some extra electrons sitting at the boundary, and that's the bulk edge correspondence. And so we can actually work this out explicitly. You can look at these slides later and work it out yourself if you haven't done it before. But if you take the Hamiltonian on the previous slide, we want to write down a low energy theory. So we should expand around the smallest place where the gap is the smallest, that's around k equals pi. And we also have to expand around this parameter delta being small just to get a simple theory. And then the Hamiltonian becomes greatly simplified, and it looks like this in terms of the sigma x and sigma y matrices. And so then to get this domain wall between these two regions, we should set this parameter delta to be spatially dependent. So on one side, it will be greater than 0, and on the other, less than 0. So delta should look like this. When we do that, this Hamiltonian is no longer translationally invariant because it has this defect. And so instead of writing k here, we replace k with minus I dx. With all those substitutions in place, you can actually exactly solve for a 0 energy eigenstate. This is the solution. It's localized at 0 energy, so right in the middle of the gap. And it's also spatially localized. It's localized at x equals 0 right at this domain wall. And so if you plot this state, if you plot this wave function magnitude squared, you'll see that it's exponentially decaying, but it's localized right on the boundary, and its energy is in the middle of the gap. And so this is an example, kind of the earliest example of the bulk edge correspondence. It's a surface state or a domain wall state between these two different phases sitting in the middle of the energy gap. So now we can take this same logic and go up one dimension. So this next example is called the Phallus charge pump. So now we're going to keep our 1D system, but add time. So what am I drawing here in this picture? I'm trying to draw a bunch of positive charges. These would be the atoms in our one-dimensional system. And then these minus charges would be electrons or electron wave functions where they're localized. And so imagine some system where we change some parameter in the Hamiltonian and we cause the electron charge to move. So this would be at time 0. And then at some later time, the electron charge has moved over by half a unit cell. That would be like moving between these two phases of the SSH chain. So the polarization is changed by E over 2. And then we keep going. And at some final time, which I call capital T, the electrons have moved over by an entire unit cell. And so in this process of charge pumping, the initial and final configurations are completely the same, but something has changed because the electrons have moved over by half a unit cell. And notice that the initial and final configurations are only the same in an infinite system. In any finite system, there'd be a little bit of a lag, like in my picture, where there'd be some charge left over. But in an infinite system, we can't tell the difference. But what is well defined is how much the polarization has changed. And so we can ask the question, how much charge is pumped in one full cycle? So as we go from time 0 to time t, what happened to the electron charge? And so we can compute this as the change in polarization. We can say the change in polarization is given by the integral over time of the derivative of the polarization. So that will give us P final minus P initial. And then we can plug in our definition of polarization. And as we saw before, see that we'll get the curl of the Berry connection. But we also know the answer, how much charge is pumped. There's just one electron, because what we've done here is we've moved the electrons all over by one unit cell. And so we can see here that since we know the change in polarization is 1 electron, it must be that this integral here is giving us 1. And if we say we pumped our charge twice as fast, as long as the initial and final configurations are the same, we could only get some multiple of 1 electron here. We could never get a fraction as long as the initial and final configurations are the same. So this integral, no matter what our pumping is, this integral must give us an integer. And this integer is what's known in condensed matter as the Chern number. So this is the same integer we'll see momentarily that comes back to the quantized Hall conductivity. So formulaically, this is the definition of the Chern number. And although this is a complicated looking integral, it always has to give us an integer. And one way to think of it is to think of this charge pump system. As long as your initial and final configurations are the same, then you can only have pumped an integer amount of charge. And so the takeaway, or what I want you to take away here, is that the Chern number is some topological invariant given by this formula. It always gives us an integer, and it characterizes wave functions in 2 dimensions. And so in this case, our 2 dimensions are our 1D system, so K, and time. But in the quantum Hall case, those 2 dimensions will be 2 spatial dimensions. And if you know your wave function, this is something that you can just compute. It may not always be easy, but you just have to compute this integral. It's something concrete. So the Chern number is some 2D topological invariant, but I think for me, it's helpful to think of this as how much the Berry phase winds. And so if we take apart a little bit more of this formula for change in polarization, we can write this as the integral in time over the derivative of the Berry phase with respect to time. And so integral of derivative just gives us the Berry phase at time t minus the Berry phase of 0. We kind of knew this because change in polarization should be proportional to change in Berry phase. And so this actually gives us a practical way to compute the Chern number, which is very convenient numerically. Instead of doing that integral that I showed on the previous slide, what you do is you compute the Berry phase, say at some time, and then plot that Berry phase as a function of time. And you can see a Chern number of 1 means that the Berry phase, instead of returning to its original value, say goes from 0 to 2 pi. So this is a practical way to compute the Chern number by thinking of it as a Berry phase in one direction, plotted as you move some parameter in the other direction. And just for comparison, I want to show what the trivial case would look like. So a Berry phase of 0 would mean you make the same plot, but you come back to your original starting point. There's no winding around. And similarly, if there is a Berry phase of 2 or winding of 2, this would mean you go around twice, etc. And so this is, like I said, a practical way to compute the Chern number. And if you're wondering how to rigorously define winding, what you can do is just draw a straight line across here. And you can see that if you draw a straight line anywhere in the spectrum, the number of times it crosses a band with positive slope minus the number of times negative slope will give you this winding. So here we cross 2 lines, so that gives us a winding of 2. But here we wouldn't cross any, so we could get a winding of 0. Or if we drew a line down here, we'd say we cross positive slope and negative slopes. That's also a winding of 0. So no matter how complicated this plot is, you just draw a straight line across it, count how many bands are crossing with positive and negative slope, and that's a way to get the Chern number. So now we can come back to this quantum Hall physics. And so we can understand the integer quantum Hall effect through what's known as this Laughlin flux argument. So this is how the argument goes. And what we're going to try to do is show why the Hall connectivity has to be quantized. So the picture is like this. This 2D cylinder is our quantum Hall system. So remember, quantum Hall is describing 2D electrons in a magnetic field. And so now we're going to take that system and wrap it into a cylinder. And then we're going to thread some magnetic flux through the center of the cylinder. And so you might be worried. Our initial quantum Hall system was 2D, and it had the magnetic field perpendicular. In this new configuration, the magnetic field is not perpendicular, it's going through a hole in the center, but we could make the same argument by taking this cylinder and kind of flattening it out, and then the magnetic field would be going perpendicular through a hole in the center. But ultimately, we're making a very fundamental argument here for why Hall connectivity should be quantized, and the geometric configuration doesn't affect that argument. Okay, so let's go on. So the idea is that we're threading a flux quantum, 1 unit of magnetic flux. So at time 0, there's no flux, and at some final time t, there's exactly 1 flux quantum going through the center of this system. So by Faraday's law, we know that there's going to be some EMF, electromagnetic force, which is when you have a changing magnetic field, which is changing in time, there's going to be an EMF around this. And that change in potential is going to generate an electric field. So there's some electric field which is going around the cylinder. And then by definition of the Hall conductance, the Hall conductivity tensor is relating how much current you get along the cylinder related to the perpendicular electric field, which is now around the cylinder. And so if we plug in this expression for electric field, then we see that by definition of the Hall conductance, we get that the current density is given in this way, and it's related to the time derivative of the threading of this flux quantum. And so then we can ask, how much charge is moving from the left to the right-hand side of the system as we thread this flux quantum? Well, current is going along this way, and current is carrying charge. So we can say the change in charge, which is the total charge pumped from the left to the right side, is given by the integral of current over time. And since the current is given as the derivative of the flux through the cylinder, we can plug this expression for current into here. And then we see that the total charge, which is pumped, is proportional to this Hall connectivity tensor, and the constant of proportionality is this quantum of h over e. So this is all just plugging in formulas carefully. And then finally, there's some final step, which is that if we assume that the system is insulating, then this process of threading 1 flux quantum, we can always gauge away 1 flux quantum. So the eigenstates must be exactly the same at time 0 and at time t. Maybe now you see the comparison to this Phallus pump. We did some procedure, but at time 0 and time t, capital T, the system is exactly the same. All the eigenstates are the same. So the only thing that can change in this process is that the occupation number of these eigenstates can change. And the way that occupation number changes is that some charge on the left-hand side is now moved to the right-hand side. But since all of these states can only host either 0 or 1 electrons, we must conclude that the total charge pumped must be an integer number of electrons. We don't know what that integer is, but it must only be an integer. And so that tells us that this change in charge, the left and the right-hand side, must be an integer number of electrons. And so then if we relate these two expressions, we can see that the Hall connectivity is an integer multiple of this quantum e squared over h. And so through this argument, which relies only on gauge invariance, we see that if we have an insulating system, the Hall connectivity is restricted to taking integer multiple values of e squared over h. And this explains the quantization of the integer quantum Hall data that I showed at the beginning. This is valid for any insulator. So in some system without a magnetic field, this integer n could be 0. And then as we vary the magnetic field, that changes the Hamiltonian, and that changes this value of n. But the logic here is showing that n must take on integer values for any insulating system. And so now we can compare this to the TK and N invariant that I showed earlier. And then what we have to deduce here is that this TK and N invariant, if we write that formula, so the formula there was written in terms of the cell periodic parts of the block wave function U, but if we translate all those derivatives, we can see that we can write that as the curl of the Berry connection. And so, so that TK and N invariant has to be quantized by the logic that we've just been talking about. The curl, this integral of the Berry curvature always takes on an integer value. And so now we have two ways of understanding this. We have this Laughlin flux argument, which uses gauge invariance and says that Hall conductivity has to be quantized. And then we also have this explicit calculation by TK and N, which amounts to some integral, and that integral also has to be quantized. But the integral gives us a concrete way to compute the Hall conductivity. This Laughlin argument just says it has to be quantized, but you won't know what value it is until you actually compute this thing. And so this, to make the connection to the Phallus pump, that churn number that we saw in the Phallus pump argument, which is as a function of the 1D wave vector and changing the Hamiltonian in time. Now here we have a 2D system. And so the churn number is actually in momentum space. That two parameter system is kx and ky. And so we can think about if you computed a Berry phase, say around the ky direction, and looked at how that Berry phase changed as you vary the starting point kx, you would see some change in Berry phase, and that change in Berry phase would give you a churn number in the way that I was just showing on the previous slide. So coming back to the bulk edge correspondence, the churn number gives us a surface state, and we can understand this. In different ways. We can compute the TKNN invariant in the bulk, or we can look at the surface states. And in the end of the day, we'll get some plot like this, where we see, like I showed earlier, there's one extra state connecting the valence and conduction band if we plot our band structure for a finite size system. And so since that state does not appear when we plot the band structure in a bulk system, we deduce that this state has to be localized on the edges. And the other thing that I want to emphasize in this bulk edge correspondence is that frequently this is drawn straight, but it's not, in reality, it's not going to be some straight line connecting the conduction and valence bands. It can have some curvature, and it can even go up and down like this. So the actual dispersion of a surface state is determined by surface physics, but the bulk edge correspondence tells us that there has to be some state which is connecting the valence and conduction band. If you have a churn number of 1, if you have a churn number of 2, there'll be 2 states, etc. So then in the last couple of minutes, I just want to say how this extends with time reversal symmetry. So time reversal symmetry is some anti-unitary symmetry, which will, it commutes with the Hamiltonian, but if we diagonalize the Hamiltonian with respect to these block wave vectors k, it takes a state indexed by k to a state with minus k. And it also has this property that the time reversal operator squares to -1. And so this means that at every k, which is the same as minus k, so i.e. k equals 0 or k equals pi, these are known as the time reversal invariant momenta, there has to be 2 degenerate states, which is a state and its time reverse partner. So from this logic, we can immediately see that time reversal symmetry is inconsistent with having a churn number, because we just said that a churn number should give us a surface state like this, but time reversal symmetry would require at k equals 0, there has to be a partner like I've drawn here. And so having a churn number is inconsistent with time reversal symmetry. And actually we could see this because if we computed the action of time reversal on the Berry curvature, we would see that it's odd. And so if we integrate the Berry curvature to get the churn number in the presence of time reversal, that integral must be 0. So the bottom line is that in the presence of time reversal symmetry, you can't have a single surface state, but you can have surface state partners. And this is exactly the definition of a 2D topological insulator. So in a Chern insulator or quantum Hall state, you'd have just one of these chiral edge states or multiple. But in a topological insulator, you have states which are moving in opposite directions, and they can't gap each other because they're time reverse partners. So time reversal symmetry is protecting them. And so this gives us a notion of what's called a Z2 topological invariant, which is we can ask, are there an even or an odd number of bands? So I said before, to compute the Chern number, we could draw a straight line across, and we could see how many bands are we crossing with positive and negative slope. Well, if you have time reversal, you'll always cross an even number of bands, and you'll always get Chern number 0. But you can make a modification, which is to just look at half the Brillouin zone, because if you have time reversal symmetry, K and minus K are related. So if you just look at half the Brillouin zone, then you can just count the number of states which are crossing some line over half the Brillouin zone, and you can ask if there's an even or an odd number of those. And if there's an odd number, then that means you have a 2D topological insulator. And so similarly to this TKNN invariant, there's also a bulk invariant to compute this, the Z2 TI index. But similarly to the TKNN invariant, it's very hard to compute. So this is the explicit formula. You can see it's written in terms of these cell periodic wave functions, but in practice, it's ideal to avoid computing this invariant. So I guess what I want to emphasize is we can compute, or we can classify 2D TIs by their surface states, but in practice, we don't actually want to compute the surface states. We want to compute things in the bulk, because that calculation is computationally simple. So we have this bulk invariant, but it turns out that this is quite difficult because you need to choose a continuous gauge across the Brillouin zone. And so there's, again, a practical way to compute this Z2 invariant, which is to compute the winding of the Berry phase. So I previously showed to get the Chern number, you could see how does your Berry phase wind as you vary some other parameter. But here, what we want to do is look over half the Brillouin zone. So say take the Berry phase going from 0 to pi, or in this case, minus pi to 0. And then we can ask the same question. If we just look over half the Brillouin zone and draw a straight line, how many times do we cross this Berry phase? If we cross it an odd number of times, then we have a 2D TI. And if we cross it an even number of times, like on this right-hand plot, which could be 0, or it could be crossing twice, then we have a 2D trivial phase. So this is one practical way to compute the Z2 invariant. And I also just want to point out that I've kind of gone back and forth between plotting the Berry phase winding as a function of some parameter and plotting the surface states. And actually there's a rigorous connection between these, which is outlined in this paper, in this reference.
Jen?
Yeah?
I have 3 questions.
Great.
Okay, so the first one from Mark Villa. You mentioned in the 1D case that only when the unit cell is not polar, the Berry curvature is finite. Does this apply also in 2D and 3D?
Right. So the Berry phase in this is kind of it's a 1D result, because you're always going to compute the Berry phase in one direction. And that will give you the polarization in one direction. But yes, if you computed the Berry phase in X and then computed it in Y and then computed it in Z, same thing. You could get the polarization in all those directions. They would just be computing Berry phases in different directions. The Berry phase has an orientation because you're making a closed loop in momentum space, and you need to choose whether that loop is going to be going around X or Y or Z. So it generalizes to 3D in that way.
Okay, then from Richen Chion, when we calculate the Hall conductivity, we calculate the Chern number of the bulk band. Why don't we need to consider the Chern number of edge state dispersion?
Right, exactly. So that's a good question. This is the whole point. This is the whole point of the bulk edge correspondence. So the Chern number is defined for a 2D system with two parameters that we can make closed loops around. And so that necessitates periodic boundary conditions in those 2 parameters. So I would say the Chern number is something you calculate for a 2D bulk. By bulk, I'm meaning of a 2D material. And the edge state dispersion is a consequence of that. So there's 2 calculations you could do. One is Chern number in the 2D bulk, and the other is plot the edge band structure and look for edge states. But it doesn't make sense to compute the Chern number of the 2D edge because the Chern number requires 2 periodic directions. And once you make a finite edge, you don't have 2 periodic directions.
Okay, and then from Umesh, can you repeat the last point again about topological insulator having surface state protected by time reversal symmetry?
Yeah, so right, let me just say, there's 2 points I'm trying to make. One is that if you have time reversal symmetry, you can't have a Chern number. But if you have time reversal symmetry, you can have something enhanced, which is you can have 2 surface states. Ordinarily, if you had no symmetry at all and you had 2 surface states, these things could gap. But time reversal symmetry protects this gap from opening because the 2 states here are time reverse partners. So they're related by symmetry. So you can't change one to one energy and another to another energy. So, right, so that's the point, that time reversal symmetry has the capability of protecting surface states which cross. And if you didn't have time reversal, this would generically gap. And the overarching feature here is that symmetries can protect surface states. And so if you add more symmetry, then you can get enhanced or different classifications.
And the last one is something that I think you explained already, but it's from an anonymous attendee. What is the difference between Zac and Berry phase?
Yes, good. So the Zac phase is Berry phase over the Brillouin zone. So Berry phase is a very general concept, which is how do wave functions change as you vary some parameter. Zac phase was just to say, look, that parameter that we vary can be k, the wave vector. So instead of varying some external object, you have some Hamiltonian, it's a function of k, and you treat k as a variable, and then you can make a closed loop around the Brillouin zone. And it's closed because you can go from 0 to 2 pi, and those points are the same. So yeah, Zac phase is just Berry phase around the Brillouin zone. And much of the time, people just call it the Berry phase if the context is obvious.
And the last one, are these last plots of Berry winding numbers the same as Wilson loops?
Yes, these are exactly the same. So right, so I think that Titus is going to cover this later in the week. But yes, this is the exact same thing as the Wilson loop. And just to say, for people who are in the know, or have seen this before, there is one little thing which I swept under the rug here, which is actually, we've been talking about the Berry phase just for one band, which is like UDU. If you have multiple occupied bands, which you always do for a TI, then that Berry connection should become a matrix. It'll have indices that depend on the band, the occupied band. So it would be like UN, DUM. And that will give you what's called a non-abelian Berry phase. And that will give you Wilson loop plot with multiple lines like this. So yeah, I'm not going to say anything more about it, but the answer is yes, those things are the same. Good. So let me just show a couple of more slides so we don't run over too late. So the other thing that I want to say here is that if you have extra symmetry, it's even easier to compute the Z2 invariant. So there's 2 cases that I want to mention. One is quantum spin Hall, which is if you have spin conservation, if your 2 spins don't mix in your Hamiltonian, you can compute Chern number for spin up and Chern number for spin down. And that will give you the Z2 index in that special situation. The other situation, which I'll talk more about tomorrow, is if you have inversion symmetry, then you can compute the inversion eigenvalues at these trim points. And this is actually the method which is used in practice the most. Instead of computing that more complicated formula that I showed, you just look at all your trim points and compute the inversion eigenvalues and multiply them all together. And since inversion eigenvalues are either even or odd, +1 or -1, their product is also +1 or -1. And if that product is -1, then you have a non-trivial Z2 invariant. So let me just skip ahead to kind of the last thing, which is that in 3D, what's the analog in 3D? In 3D, it turns out that you have 4 Z2 indices, which are called strong and 3 weak. And this corresponds to having a Dirac cone on the surface if your strong index is 1, or for your weak indices, you have 2 Dirac cones on the surface. And we can understand this, what's called a weak 3D TI. If you stack a bunch of 2D TIs, each one in this stack will contribute a surface state. And so you'll end up with multiple Dirac cones. But this thing requires translation symmetry. If we broke translation, which would cause us to fold the Brillouin zone, then these Dirac cones would gap each other. And so that's why these are called weak indices. The strong index doesn't have that property because it's 1 Dirac cone, so you can't gap it by breaking translation symmetry. And one way to think of this in an analogous construction is that if you have a kz equals 0 plane to be a 2D, say a 2D TI, and the other planes to not be, then this would give you the appropriate surface states, but it manifestly doesn't really have anything to do with translation symmetry. So the slides that I skipped are having to do with experimental realizations. So you can look those up and look back at these slides and look up those references. But the last thing that I want to say is that, because this leads into tomorrow, I've talked about Chern number, which requires no symmetry, and time reversal symmetry, which gives us 2D and 3D TIs. What else is there? Well, the famous classification of these is called the tenfold way classification. The classification is quite technical. You can look at the reference here, but the point is that topological phases in any dimension with either time reversal or charge conjugation, which is particle hole symmetry, or both or neither, these have all been classified. And so just to show some examples, these are the examples we talked about. So there's these different symmetry classes which tell us, do I or do I not have time reversal? And if I do, does it square to +1 or -1? And same with charge conjugation. There's 10 combinations of those. Class A has no symmetry. In 2D with no symmetry, we have a Z invariant, and that's our integer quantum Hall invariant. If I look at this class A2, which is the class of time reversal symmetry in electrons, if I look at 2 and 3D, I get this Z2 invariant. So these are the 2D and 3D TIs that I mentioned. And all these other classes are about topological superconductors, and some other classes. All of these are with on-site symmetry. And so tomorrow, what we'll talk about is adding crystal symmetry and see how that enhances classification. Okay, so that's everything I want to say for now. Maybe there's time for 1 or 2 questions, or maybe we should just put it on Slack. That's up to you guys, Maya.
No, sure. There is one question from Chiara. Can the Wilson loops always detect topological edge states?
Great question. So like I said, there's this correspondence between the Wilson loop spectrum and edge state spectrum. So for 2D TIs and some other examples, then the Wilson loop spectrum can tell you about the edge state spectrum, and that's robust. Once you start adding crystal symmetry in, it becomes a lot more complicated. It's not, for some cases, it's not always clear what the right Wilson loop calculation would be. And also it's not clear that you would have surface states. So maybe I answered I think the answer to your question is that yes, the Wilson loop spectrum is in topological correspondence to the edge state spectrum. But in either case, the Wilson loop or the edge state spectrum doesn't always tell you the nature of topological states with crystal symmetry, but yes, they do always correspond to each other.
Okay, and another question is, could you please elaborate on your comment on the topological nature of the SSH model?
Yes, right, I can elaborate on that. So one of the things that I'll mention tomorrow, so I won't bother skipping back to that slide, but the comment that I made earlier was that should we call the SSH model a topological phase or not? And these Chern number phases and 2D and 3D TI phases, one of the things that makes them topological, I would argue that this is the definition of a topological phase, is that you cannot deform that phase to an atomic insulator. If I try, it's an insulating phase, but if I tried to, say, pull atoms apart and make a model with completely trivial flat bands, I wouldn't be able to do that because those phases lack exponentially localized Wannier functions. They're completely unvannierizable. there's something different about the SSH chain, which is in 1D, there's two different models, delta greater than 0 and delta less than 0. And each one of those is actually an atomic limit. We can think of it as having electrons situated in one spot, but the difference between the two models is that in one case, the electrons are at x equals 0, and the other, they're at x equals 1/2. So there's no notion, like electron Bonnier functions exist and are localized in that model, but the two models are different. And so I would say that that's a topological phase transition because there's a quantized invariant, which goes from 0 to pi, but neither phase is actually a proper topological phase because it can be thought of as a band insulator. It has exponentially localized Bonnier functions. And actually, this should be, in one sense, it's a little bit obvious because changing delta from less than 0 and greater than 0 is a translation by half a unit cell. So there's no notion in which these things are, there's no way one could be topological and one couldn't, but the transition between them changes this very phase invariant.
Okay, and the last question, following the Wilson loop, it's correspondence. Does this mean that if a system has a Wilson loop that has no gap, it will have a topologically protected edge surface state?
Right, so there is one subtle thing in this, which is that these, the Wilson loop surface state correspondence is, they don't need to be exactly the same, but they need to be topologically the same. So what that means is that it would be possible, like for example, let's look at this picture on the right. The Wilson loop shows gapless state here and gapless state here. The surface spectrum might not have this surface state because this state, it might be moved up. You know, suppose this was a band structure and suppose this was the valence bands and this was the conduction bands. In the edge state spectrum, there's nothing that pins this to 0. So these states could be way higher in energy and therefore completely disappear. So there's not a one-to-one correspondence, but there's not an exact correspondence, but there's a topological correspondence. The topological attribute in this picture is that if I draw a line from 0 to pi, I will cross the edge states an even number of times, which may be 0 or it may be 2. That's what the correspondence is. But it may be possible that the Wilson loop spectrum has a gapless state, which is not present in the electronic edge state spectrum because there's nothing that fixes the edge states to a particular energy. Yeah.
Okay. Thank you, Jen. Okay, so we take a break and we reconvene at 5 p.m. Central European time, 11 a.m. in New York, I think. Okay, see you in the 20 minutes. Thank you, Jen.
Hi, can you guys hear me?
Yeah, hi, Andre. Yes, we can hear you.
Very good. Okay, I just wait 4 minutes.
Yes.
Okay, fantastic. Thanks.
You can share your talk if you want.
Is working?
Yes, it's working. This is your first slide. All the pictures. Okay.
The first slide.
Yeah. So you thank everybody. Okay, I'm gonna start recording whenever you share it.
Hi, Andre.
Hi, I was just going to send you a private chat.
How's it going?
Andre, can you share full the screen?
You mean full screen?
Yes.
Yeah, I can.
Oh, okay.
I'm private chatting with Adolfo at the moment, so.
Can you privately ask Andre to share?
Okay, sorry. Hang on, let me just quit my, 1 second. Okay, how about this?
Thanks.
Thank you.
Okay. Okay, I'm gonna start. Sorry. Okay, so we wait 1 minute and we start. All right, so welcome everybody to the afternoon session. We are very pleased to have Andre Bernevik to give the last lecture of today. He's gonna talk about flat band principles in Moire and stoichiometric compounds. So Andre, welcome to the online school of San Sebastian.
Thank you very much. And hopefully soon we'll be able to do it in person. Okay, so this is going to be a talk given in 3 series about flat bands in Moire in the first 2 parts, and then the stoichiometric compounds in the last part. And before I start, I basically wanted to say that the principles involved in this talk have been found in a collaborative effort with basically all these researchers over the past more like 5 or 6 years. So the first row is the junior people, the second row are the senior people, and I'll be basically talking about their work here. So the 3 parts are the following. in the first part, which would have overlap with the previous two talks, but which will also use methods from the Kano and Neupert series that's coming, is going to be to sort of understand the single particle flat bands in twisted bilayer graphene from a sort of momentum space topological viewpoint. I think Vafek will talk about the real space picture of these bands. Then I'll talk in the second part, hopefully, about the effects of the interactions on these flat bands. And this part will have overlap with some things that you'll learn in the Vafek and Repellant talk. And the third part, I'll be talking about flat band methods, methods to basically generate flat bands beyond Moiré. Sort of the Moiré method is, can be interpreted as part of these methods. But these would work in stoichiometric compounds also. They're kind of a generalization of the Lieb method, and they allow us to make a catalog of flat bands in stoichiometric 3D compounds rather than just two-dimensional compounds. Okay, so let's start. So basically, why are we interested in flat bands? Well, sort of the principle, in retrospect, kind of looking back, people were interested in flat bands because the kinetic energy is quenched and you have strong correlations. But more recently, the type of flat bands that we're interested in is turn out to be topological for a reason that we'll go through in the third part of the talk. It turns out that there's a high probability that if you find a flat band without zero hopping integrals, or with non-zero hopping integrals, there's a high probability that will be topological, and I'll tell you the reasons why. It turns out that almost all the topology that we've known before the flat bands was sort of non-interacting. If you look at topological insulators and topological superconductors, they all kind of have an expression in terms of a quadratic Hamiltonian of fermions, and we really didn't know an example of interacting topology, with the exception of the quantum Hall, of the fractional quantum Hall effect, which is the kind of quintessential type of topologically strongly correlated state, but that requires, of course, a strong magnetic field. So we really didn't know how to marry the two, these two parts of physics, correlations and topology, and what would be the interesting phenomena that are coming out of a system that has both correlations and topology. So that's why we as a field, have found the discovery by Pablo so interesting, because it, in the end, in retrospect, you can also see that it kind of marries these two concepts. Okay, so topology, non-interacting topology, has been known for a while to give new types of excitations, and the excitations that we'll be talking about in today's lecture will be basically Dirac fermions. And these Dirac fermions were, of course, first seen in the remarkable discovery in graphene by Gaiman Obaselov of single layer graphenes. It turns out if you take a hexagonal arrangement of atoms, of actually PZ or S orbitals, atoms on a hexagonal lattice, and Fourier transform to momentum space, you are going to get a Brion zone, a hexagonal Brion zone that has two special points. In this case, it's got more special points. It's got the gamma point and the M point, but the special points that we'll be focusing about in this on this slide are the K points. And of course, you invariably are going to get Dirac nodes at these points if you start with S or PZ orbitals sitting on the hexagonal sites. You're going to get Dirac points at the K and K prime point, and that will be explained, I guess, by Kano in her talks. But what I want to point out is that there's a huge amount of topology already in this in this very simple model. So, for example, you can ask questions like, why do the Dirac fermions show up in pairs? They always show up in pairs in K and K prime. You can ask what's keeping this degeneracy here from splitting. You can ask, why are these guys kept at the corners at the K and K prime point? Why don't they move about? And all these questions really have a symmetry answer, or a topological, should I say, answer. And you can then ask, even further questions like, what is there some characterization, some number that characterizes the Fermi surface of a Dirac fermion? And the answer to that is yes. So basically, we're just going to go very quickly through them. What keeps the Dirac nodes from splitting is a symmetry called C2 rotation by 180 degrees around the z-axis, which sends K prime into the K point, but then you act again with time reversal, and this sends it back to the K prime point, or to the K point if you started. So this is local symmetry in momentum space, and it turns out that in 2 dimensions, it protects Dirac nodes. The reason why there's 2 Dirac nodes and not 1 is called the doubling theorem that I'm sure a lot of you heard about. And this doubling theorem basically says in 3 dimensions that Weyl fermions cannot appear but in pairs. And in 2 dimensions, it says that Dirac fermions, which are protected by this symmetry, can then not appear but in pairs. And so that's a doubling theorem. Then what's holding these Dirac fermions at the corner? Well, that's C3 symmetry. If you break C3 symmetry, you'd be able to move them about. But still, this C2Z, the C2 times T symmetry would locally protect the Dirac fermions. So what I'm trying to point out here is there's a huge amount of symmetry arguments that basically can explain this universal property that if you put S or PZ orbitals on a hexagonal lattice, you're going to get Dirac fermions. Now, what's a way to kill this doubling theorem that you have in 2 dimensions? Well, topological insulators actually do that. And you can sort of understand topological insulators as taking one of these Dirac cones and moving on the upper surface of a 3-dimensional sample, and taking the other one of these Dirac cones and moving them on the lower dimension, on the lower surface of a 3-dimensional sample. And you can, of course, as I said, not do that in purely 2 dimensions because there's a doubling theorem, but you can do that in 3 dimensions. Okay, so I hope I convinced you that there's a huge amount of symmetry here. So how do we do to marry sort of topology and interactions? Well, the simplest way in retrospect, so again, these are all retrospective comments, is to basically take a system that's got topology, such as Graphene, which has got these Dirac nodes, and which alone doesn't do a lot of interacting things. It does some, but not a lot of them, because the density of states is very small at the Dirac point, and sort of do something to its bandwidth, which is electron volts, to make the bandwidth as small or smaller than the interactions. Okay, and this brings us to basically a new scale in the physics of these systems. By the way, please, I'm not sure how it works, if you can interrupt while the talk is going, but and I'm not sure what the policy is, but well, I guess do what they told you in the policy, but I don't mind if you interrupt me while the talk is going. Okay, so as I said, making these samples where the interactions are kind of competitive with the hopping requires going to a different length scale. And why is that? Well, if you take material chemistry, which has an inherent scale, stoichiometric materials have inherent scales of few angstroms, generically, you will get hopping integrals or bandwidth of order electron volts. And I'll show you in the last part of the talk that for special systems, then you can kind of go through high throughput and find them. That's not true, but generically it is true in the sense that, you know, for 90% of the cases or 95% of the cases, or it's true. Now, there's another length scale, which is that of optical lattices, which is much larger than the graphene lattice. And this is the cold atoms optical lattices scale, in which this length scale about a micron. But in between them, there's this length scale that, you know, people like Emmanuel Tutuk and Pablo and others have exploited in the past, which is the Moiré superlattice scale, which basically is of the order nanometer scales. And this is really a way to get flat bands or a high density of states from still crystalline materials by doing a little bit of engineering with them. Okay, so here what you have is an example of such a Moiré lattice under different deformations. So this was, you know, some version of this was showed in the previous talks, but basically what you do is you take a layer of graphene, you put another layer of graphene on top of it, and then you twist it by a small angle. But you can do more than that. You can, you know, twist it, you can strain it, you can strain it in different directions, you can compress it, you can slide it, etc. And all these things, for example, create deformations of the lattice, and you know, you can write a small Mathematica code that gives you exactly how the lattice deforms and how a superstructure arises from these deformations. Okay, so the interesting thing, of course, was that when this was done in Pablo's group, they found an amazing array of interacting states here that we're going to get to. But first, let's kind of understand what happens when you take two layers of graphene and twist them with respect to each other. Of course, this is kind of a review of what was shown in the previous talks, but we'll take a different angle in the next slides. So very shortly, and this, you know, you can find this explanation very clearly in these papers. What happens is that we know where the physics of the lower layer of graphene and the physics of the upper layer of graphene happens. The physics of the lower layer of graphene happens around the points, you know, K1 and KY1 prime. So we call one layer the layer 1 and the other layer the layer 2. Okay, so this is where you have a Dirac fermion in the lower layer, and this is where you have the other Dirac fermion that I said is necessary by lattice doubling in the other layer. Now, when you add in the same layer, but in the other valley. Now, in the other layer, you also have a K point with a Dirac fermion and a K prime point with another Dirac fermion. So now you have, of course, two Dirac fermions per layer, 2 layers. You have 4 Dirac fermions. But what turns out to be the case is that if this angle is small, if the angle between the two twisted layers is small, then you have a phenomenon which is basically called valley decoupling, which means that if you couple these layers, if you couple layer 1 with layer 2 through hopping integrals, so this so far is just single particle physics, if you couple them with hopping integrals, what will happen is that you're going to create a small, you know, called Moiré-Briand zone, which is a new periodicity, this large periodicity in space, a new periodicity. And here is exaggerated because this angle here, you know, here is probably 10 degrees or 12 degrees drawn, but in reality it's 10 degrees, it's 1 degree. So it's much smaller than this. You just can't see it if I would draw it like this. Okay, and basically what happens is that the probability of tunneling between the physics given by the Dirac fermions at K of the lower layer and K of the upper layer, and the Dirac fermions at K prime of the lower layer and K prime of the upper layer, so doing this, is kind of proportional to, there's some path factor which I won't give it, it's kind of proportional to the interlayer coupling W over the intralayer hopping to the distance between the K points, so K minus K prime, over the distance between the small K points, which we call moire. So this distance here is just this distance, is this distance. And this distance here is basically this distance, okay? And this just comes out from perturbation theory. In order to couple these values, you need to basically tile this Brillouin zone perturbatively an amount of times to get to the other K point. Now, this is a large number. It's of the order, this number is of the order 1 over theta. W is smaller. W is the interlayer hopping. Is smaller than the intralayer hopping by factors of 10. So this is an exponentially suppressed number. So what happens is that you have a valid degree of freedom, and this valid degree of freedom basically tells you that you can look at the physics of the system of this twisted layer as the physics around one valley, which comes from the K point of the upper layer and the K point of the lower layer, and of graphene, and decoupled in the non-interacting case. They'll couple interactively with interactions. Decouple the physics from the other valley K prime. Okay, so let's look at the physics within one valley. As we said, you have this is the K point of the layer 1, and this is the K point of the layer 2. Okay, and if the interlayer hopping is much smaller than this distance, this energy scale, okay, which is this energy scale is basically the Fermi velocity of the Dirac fermion times K theta is basically this momentum difference, is the small Moire-Brillouin zone momentum difference. If it's smaller than this, then you basically just have two Dirac cones, one on top of the other. Nothing very interesting happens. However, this is tunable, this K theta, because K theta is proportional to theta, okay? And it's tunable in such a way that you can make theta small. And hence you can tune it so that you have the following condition, that the interlayer hopping is basically of the same order of magnitude or equal to the Fermi velocity of the Dirac fermion times this momentum difference, which is basically, this momentum difference is basically the characteristic length scale of the Moire-Brillouin zone, okay? Or the characteristic momentum scale of the Moire-Brillouin zone. And then what happens is that invariably this difference becomes important, and you have a manifold. You have basically the Dirac nodes flattening their velocity, okay? You have this doing this and getting less and less dispersive, and at the end, the Dirac nodes have flattened their velocity, and you get flat bands. Now, there's a further, more subtle flattening that even at small angles, some angles are special, and these are called as magic angles, which you need to go through the approximations of the model to fully understand them. But I'll give you a more generic picture in terms of line graph lattices. Later, it turns out that you can write the graphene tie binding. You can write a graphene tie binding model if you neglect some symmetries, a twisted bilayer graphene tie binding model if you neglect one particular symmetry called particle hole, which basically makes it so that you have exact flat bands and the system is, and the model is a line graph, which I'll come back to later. Okay, so we argued that small angle should have flat bands, or bands that are much flatter than the original bands. But how flat are they? Well, if you look here, you can see these plots which were already shown in the previous talks. You can see these plots. These are some plots at, for example, I guess this plot includes relaxation, which is just from this paper by Koshino et al. And these bands are basically incredibly flat compared to the other bands, and we call these the active bands. These will be called active. Okay, and how many active bands are there? Well, there's a bunch of them. There's actually 8 active bands. And why are they 8? Well, you have, as I said, 2 spins. So there's a spin degeneracy. You consider low spin orbit coupling, and you have 2 valleys. So as I said, the physics around K decouples from the physics around K prime of the original graphene. Notice that these are the K of the Moiré lattice. So they're the different Ks. For example, these are the Ks of the Moiré lattice here. This is K Moiré, and this is K Moiré prime. Okay, and K Moiré is, for example, the K of the upper, or K prime of the upper layer, and the K Moiré prime is the K prime of the lower layer, etc. Okay, so again, you have a factor of 2 from spin, you have a factor of 2 from valley, and then you know that your bands come from Dirac fermions. So there's another 2 because the Dirac fermion has 2 states. So that's 8 bands in total. And that means that as you go from a gap, from a single particle gap that's here, in this gap, filling that's here, to a single particle gap that's here, you have to add 8 electrons in between these two to, there's differences of 8 electrons per Moiré unit cell to go in between these two. Now, the Moiré unit cell is very large, so 8 electrons per unit cell is not a huge density, and you can actually tune it, as was shown by Pablo. You can actually tune it, and you can get between, this gap and this gap by just gating the system. Now, what we'll be talking about in this talk and in the other parts of the talk is the electron filling of the flat band relative to charge neutrality. So this would actually then mean charge neutrality is in the middle. So this would mean, this gap would mean -4 electrons per unit cell. And this gap here would mean 4 electrons per unit cell. Okay, and that's kind of like the accepted theory talk that you'll find in a lot of the papers in this system. Okay, so now let's go a little bit deeper into this, into the physics of these bands. And that's done, as was shown in the previous cases, by McDonald and Bisterser. This is called the Bisterser-McDonald model. And this model is, it's not, you need to work a little bit to get it, but in principle, you can argue it. And certainly the topology of the bands that I'll teach you about, you can argue it sort of model-free almost, with some constraints. But basically, the Bisterser-McDonald model is a model that takes, it's a model for these flat bands. So it's a model that basically takes the Dirac fermion it's a model per valley. So this is around the valley K, which means it uses only states at the K point of the lower layer and at the K point of the upper layer. Okay, there's a model at valley K prime, which uses states from K prime of the upper layer and K prime of the lower layer. So the model around K contains, this is the Dirac fermion of the upper layer. This is the Dirac fermion of the lower layer. And here you can see that I've made an approximation. Normally this derivative here there should be a rotation because the upper layer is rotated by the lower layer. Usually in most theoretical models, although not in all, people basically just take this model because the change by putting a rotation by theta when theta is small is very, very small to these diagonal terms. And fundamentally, a interlayer hopping, which is T of R, which is modulated at the Moiré length scale. So this T of R has modulations over the Moiré length scale, which are 10, which is 10 nanometers, so roughly of the order at theta equals to 1. And this has a particular expression. These factors, e to the IQR, are the ones that create the modulation, and the small q's, are basically the difference between the K point of the lower layer, and this is the K point of the upper layer, which are actually just become the Moiré K prime, Km prime point, and the Moiré Km point. Okay. So this is what they become. And up to a gauge transformation, this interlayer hopping is modulated at a length scale, which is the Moiré unit cell. Now, these two numbers are called AA coupling, and this is AB coupling, okay, AB regions coupling. And the reason why they're called so is because you notice that there's here this sigma in the Dirac Hamiltonian acts on the AB sublattice of the graphene, and this W0 is diagonal in that lattice, so that's AA, and this W1 is off diagonal, so that's AB. Okay, so it's a model that has two parameters, W0 and W1, and really what will be important is, what will be very important is their ratio. Okay. Okay, so how do you solve that model? Well, one way to solve it is to go to momentum space. Okay, and to go to momentum space is, instead of, you have your Fourier transform this. How does it? Let's see. Okay, you Fourier transform this guy, and you see that you're going to have a lot of plane waves. Okay, you're going to have scattering between a lot of plane waves, and for example, this is, if I keep the momentum k in the first Moiré-Briand zone, so momentum k stays in this region, then the T of R will basically give you scattering between, this point and this point, this point and this point, because of the e to the IQR. Okay, small q. These small q's are just these guys. So then this model now in momentum space is solved on a big lattice. Is actually numerically, analytically the lattice is infinite. Numerically you only need basically 3 or 4 shells to get to machine precision. So numerically, if I solve the model at angle 1 on this is momentum space lattice, by taking a lot of this many plane waves, then I already get to machine precision. And you can just diagonalize your model on this momentum lattice with K belonging to the first Moiré-Briand zone, and then you have the next Moiré-Briand zones by taking further and further plane waves. Okay, so now what we want to ask is, given that model, we want to take the route of trying to obtain kind of model independent statements and ask, we know that model has flat bands because we can solve it. Mr. McDonald did that for us. We know it has flat bands. So we want to ask, what topology, if any, do the flat bands have? And again, as I stress, it will turn out that the flat bands are topological. I'll give you a reason for it now. And it actually turns out that you test a lot of these models that have flat bands that are not atomic. Then I'll tell you what that means later, but basically it means that the hopping integrals are non-zero. So the flat bands don't come from having 0 hopping integrals. The flat bands come from having non-zero hopping integrals, but have some interference. And you find out that a lot of them, there's not all of them, we find out a lot of them are topological. So there's got to be a reason for that, and that's the reason that we'll learn in the third part of the talk. But so far, I want to basically analyze the previous model with respect to the symmetries. So I'm going to talk about the Bistritzer-McDonald models as a set of models, not just this particular model, a set of models that comes basically from taking the low energy physics of two layers and coupling them with a Moiré potential. Okay, so this for if the two layers are graphene, then and if the system keeps the symmetries that you had in the single layer, but with the extra fact that you have now a good valley quantum number, then you are left for the twisted Moiré model around the K point with the following symmetries. So C3Z is a good symmetry, and C3Z basically is a good symmetry because it takes the K point of the lower layer and the K prime point of the the K point of the lower layer and the K point of the upper layer, or the K point, the K Moiré point, and the K prime Moiré point of one valley. It takes them to the C3 times K and times K lower and C3 times K of the upper layer. And these are related to these by a reciprocal lattice vector in the original small unit cell graphene lattice. So they're basically the same points. So then if I do the physics around here, I still have C3 as a good symmetry. Okay, so C3 is a good symmetry, and this is what this symmetry does to the plane waves, to these small Q vectors that form the plane wave lattice. This is K Moiré, this is K Moiré prime, okay, etc. So this is what the symmetry does to this. It switches one into the other, okay. And then you have C2X, which is also a good symmetry, okay, of the single valley Moiré system. And C2X basically is 180-degree rotation around the x-axis and takes the K Moiré into the K Moiré prime point. Okay, that's what this symmetry does. Notice that it left, okay, the K point of the original graphene lattice invariant. Well, it switched it into the K point of the upper layer, but it left the valley invariant, and that's why it's a symmetry of the single valley Bistritzer-McDonald model, the valley around the K point of the upper layer and the K point of the lower layer. And now you have the extra symmetry that's actually the most important in this system, which is C2 times Z symmetry. And this symmetry does the following. Okay, on a single layer graphene, okay, on a single layer graphene, C2Z times T, C2Z takes the K point into the K prime point, and T sends it back. So this is a symmetry that, again, doesn't change momentum. It's the same symmetry that keeps the Dirac points invariant in single layer graphene. And it's going to be the same symmetry that keeps the Dirac points invariant in the double layer graphene, in the twisted, two-layer twisted graphene. Okay, so this symmetry, since it keeps the momentum, doesn't change momentum, is a good symmetry of the Moiré system. Notice that just time reversal by itself is not a good symmetry of the valley, of this one valley model. Why? Because time reversal by itself, even though it is a symmetry of the full system with two valleys, so you have this one, and then you have a rotated, this is the original graphene Brillouin zone. Time reversal sends the K point into the K prime point. So if your physics in a single valley uses states only around the K point of the upper layer and the lower layer, then time reversal would change it to the physics of the K points of the K prime points in the upper and the lower layer, and hence time reversal is not a good symmetry of the single layer of the single valley Moiré system. Okay, there's a question. Okay, so this is very good. There was a question, why do we need to use a magnetic point group for a non-magnetic system? It's a very good question, and this is what I'm coming to. So, as I said, if you take into account two values, then the physics stays time reversal invariant. Okay, so this time reversal sends one valley into the other valley. Okay, however, if you want to use the fact that you now have a valley symmetry, so basically if you want to use the full extent of your symmetries, the fact that you have a valley symmetry, which would actually be a large symmetry, will give you a continuous symmetry. If you want to use that, then around a single valley, okay, the physics doesn't have time reversal because time reversal switches to the other valley. So if you want to filter the valley quantum number, then the symmetry group is magnetic, is not a non-magnetic symmetry group, even though the material is in the single particle formalism, still non-magnetic, etc. So that's why you need to use a magnetic space group, okay, for figuring out the physics of the single valley filter system. I mean, it's not necessary, but it makes things a lot more transparent. Okay, I hope that answers the question. If I was to find a symmetry group for the two valleys together, it would be a non-magnetic space group, but that would miss the fact that in single particle, these states at valley k do not couple to the states at valley k prime. Okay, and the price you have to pay for just using the valley k model is you lose time reversal, but this is not essential here. You recover it by going to the other valley, and it's much easier to see the topology per valley because that's a good quantum number. Okay, so then fundamentally, so I hope that answers your question. If it doesn't answer, write another question, please. Okay, so another symmetry that's actually very important basically backtracks from the following symmetry of the Dirac fermion. So in single layer graphene, the Dirac Hamiltonian is K, okay, just K dot sigma, okay. This is with some velocity, which I picked to be 1 here. This is H of K, okay. And you can see that H of K is equal to trivially minus H of minus K, okay, just from its form. This is an approximation. It's an approximation, however, to very good accuracy. And H of K around the Dirac point is equal to minus H of minus K. Notice that this is a unitary particle hole, okay. Why? Well, particle hole, so unitary particle hole. What particle hole would do is send K to minus K, flip the Hamiltonian, and transpose it. Okay, this doesn't have the transpose. Okay, so particle hole is usually anti-unitary. This doesn't have the transpose. It's a unitary particle hole symmetry because it changes. And this basically backtracks into the two-layer having the same symmetry per valley, actually. So notice that this is the Dirac Hamiltonian of single layer graphene around one valley. Okay?
And you have another question.
Okay, sorry. Is the time reversal shown for spinful or spinless? Very good question. Spinless. You neglect spin-orbit coupling. It's a effect of less than 0.1% here. So I'll come to talk about spin-orbit coupling afterwards in a little bit. But yes, very good question. Both questions very good. Spinless time reversal. So just complex conjugation for time reversal. Okay, so you have particle hole symmetry. Okay, and this particle hole symmetry is actually a little bit weird in the sense that normally particle hole symmetry commutes with all your, the particle hole symmetry that you find in the topological superconductors, etc., commutes with all your spatial symmetries. Here, it actually turns out it anti-commutes with C2x. Okay, so it anti-commutes with this symmetry with C2x. And, we can get into the reasons for that. The reasons are actually, they all come, you can understand the reasons by looking at the single particle of the single layer and kind of mixing, putting them together to form the two layer, but it all backtracks from the particle hole of the single layer. Okay, so C3Z, C2X, C2Z times T, and particle hole. These are the symmetries. Now what we want to do as you learn, so I don't have time to go on to the reason of why really you want to do this, but you learn this in the Kahneman Neupert talks. But what you want to do once you have a symmetry immediately is to look at how the bands transform on the symmetry. And these are some generic statements about symmetries, about these particular symmetries. So for C3 symmetry, there's 3 one-dimensional irreducible representations, and they have these eigenvalues. Okay, that's pretty clear because C3 cubed has to be equal to 1, again, for the question, spinless systems. The spin is just a multiplication by 2. Now, if you add C2z times t to this system, then these 2 one-dimensional representations of C3, okay, which are complex, they basically become a 2-dimensional irreducible representation, because C2z times t, this time reverse, which is complex conjugation, flips I, so switches this one into this one, and makes the representation 2-dimensional. Now, of course, you know what this 2-dimensional representation is. It's just the Dirac node. This is the 2-dimensional representation. This is the reason why, or part of the reason why you have a Dirac node. Okay. Then, what are the eigenvalues C2x? Where C2x squared is 1. Squares to 1 for spinless systems. So the eigenvalues are 1 and -1, the characters of the irreducible representations. So now let's add particle hole into this mix. Particle hole, the particle hole that we had before, commutes with C3 and anti-commutes with C2x. Okay, so what does this tell you? Well, this tells you that if I have a state at energy E non-zero and a state of energy E minus E, because particle hole flips the Hamilton into energy minus E at minus K, but consider Ks that are invariant under K to minus K, then if this has an eigenvalue C3, this one will also have an eigenvalue C3 because P commutes with it. However, if this has an eigenvalue C2, X being 1 or -1, this guy will have to have an eigenvalue minus C2X at minus E. Why? Because, of course, P anti-commutes with this, so you get another minus sign. Okay, so now embarked with that knowledge, let's find out the symmetries of the bands at the high symmetry points. Okay, the symmetries of the bands at the high symmetry points invariably of details of the model. So now I'm not using any specific model. And what I claim is that if you take a model with all the symmetries that you have per valley, okay, so C3, C2x, C3z, C2x, C2z times t, and particle hole. If you take a model with these 3 symmetries, and assume, this is per valley, so assume the angle theta is small, then the representations of the lowest 2 bands, so the bands, the first band above charge neutrality and the first band below charge neutrality, are fixed up to some permutation. So let's find out how that is. Okay, well, that's very simple. Okay, let's see, it's another 2 questions. I don't really understand why particle hole symmetry has to be included. It doesn't have to be, but I'm including it for the reason to make a model independent statement. Then I can relax it if I want to. Okay, that's the first question. Since magnetic groups have many unitary operations, are we missing any anti-unitary ones? And we're not missing any anti-unitary one. Those are the generators of the group. So those are the generators. You can of course form new symmetry operators by taking generators and multiplying them around. Very good questions. Thank you. So, okay. Yeah, so if you want some other symmetry, some other non-unitary, you just multiply the C2ZT non-unitary with the other unitaries. Very good questions. Okay, so now let's go to the following. Let's go to this argument. So you take you take the coupling between layers to be alpha. And this alpha coupling, you can tune it from 0, okay, where the two layers are uncoupled, to all the way to the value, whatever the W0 and W1 values of the interlayer coupling, okay? I want to make this experiment where I tune this, okay? And let's see what stays constant in between these. Okay, well, at alpha equals to 0, so I just had the lower layer and the upper layer, the representations at the Moire K point are fixed. We know that there's a Dirac node at the Moire K point. There's another one at the Moire K prime point. And we know that it's got representations e to the I 2 pi over 3, okay, plus or minus these two, okay, plus minus these two states have this representation. These are the Dirac nodes. You can get the representations from the single layer graphene. They have this representation on the C3. They're fixed. Now, what you know is here, first of all, that if you change alpha, if you make alpha to go from 0 to the interlayer coupling, these representations have to be stuck at 0 energy. They cannot move. Why can they not move? Well, if you have particle Hall, if they moved, you know that if I had a representation K2 here, which would be the plus in e to the plus 2 pi I over 3, you know that if I had a plus, the K2 representation here, if they moved, and here would be the plus in e to the I plus 2 pi over 3, since particle Hall commutes with C3, here it would also have to be plus, okay? And not minus, whereas the K2, for example, is the plus, and the K3 is the minus, okay? So there's no particle Hall way of moving them away from 0 energy, or of moving a doublet, for example, away from 0 energy. If this moved all the way up here, you know, if I had them doublet here, particle will tell me I have to have a doublet here, so it would mean I have 4 states, not just 2 states, okay? So what we've learned is that no matter what I do in this process of taking 2 layers and ramping up their coupling, the representation has to be a Dirac point here, K2, K3. Then, by the same token, because particle Hall anti-commutes C2x, okay, you can find that the representation at the gamma point and at the M point, which are invariant under C2x, these are the points invariant under C2x, they have to have opposite inversion for opposite C2x eigenvalues, okay, because as we said, this flips the eigenvalue, okay. Whether this is gamma 1, you can find it here has C2x eigenvalue 1, and gamma 2 has C2x eigenvalue -1. Whether this is gamma 1 or gamma 2, or whether this is gamma 2 and gamma 1, they can flip. But the fact is, if one is gamma 1, then the other one is gamma 2. Okay, so that means that if I have 2 bands around you know, the charge neutrality point, and these 2 bands are gapped from all the other, you know, bands, so these are the active bands of the twisted bilayer, I know the representations, okay, up to this switching around, okay? So if I know the representations, what I can do, and this will, Kano and Neupert will, you know, refer to aspects of this. I think it'll be an integral part of the Kano talks. What you can do is you can, you know, put the representations in a table. Okay, this is the lowest set of bands of the twisted bilayer, and as I said, there's a gamma 1 representation and gamma 2 at the gamma point, and they're both one-dimensional. There's a K2, K3 at the K point, and there's an M1 and M2 at the M point. Okay, so you can put them in a table, and then you can go on this website that you know, part of the people that I showed on the first slide build the theory and behind it and the website, etc. Okay, you can go on this website and you can go to this symmetry group, to the symmetry group of twisted bilayer single valley, and find its atomic limits, meaning you can find the eigenvalues. There's a machinery, there's a basically just machinery that churns out given any orbitals, any localized orbitals on the lattice, it gives you the eigenvalues of these bands of the bands formed by these orbitals at the high symmetry points. Okay, so then you can go and there's a finite set of them. You can find them all on this server. They're called, basically elementary band representations. They're tabulated for every group. And if you have this set of lowest bands in graphene, you can immediately see, even by eye inspection, but there's a code given on this website of how to do it without eye inspection. But you can see clearly by eye inspection here that you cannot write these bands in terms of sums of atomic bands. So for example, if I had these atomic bands, these would be from, S and P orbitals at sitting at the center of the hexagonal lattice. So I'm asking, can I write these bands as sum of S and P orbitals sitting at the center of the hexagonal lattice? And the answer is no. Why? Because the gamma eigenvalues would match, an S and a P orbital sitting at the center of the hexagonal Moiré lattice would give you a gamma 1 plus a gamma 2. It would match. The M point would match, but the K point would not match. You can see that it would give you two K1 representations, whereas in reality you have a K2, K3 representation. And you can go through this exercise and convince yourself that there's no way that you can write down the twisted bilayer bands as sums of what's called elementary band representations, or i.e. atomic limit, localized atomic limit. So basically that tells you immediately that the twisted bilayer active bands are topological. And it also tells you that if you keep particle hole, all the symmetries, particle hole, C2, CT, and C3, etc., they are topological at any angle, any small angle. So as long as I made a small angle of twisted bilayer so that I have this valley decoupling, and as long as I have two bands disconnected around charge neutrality, disconnected from the other bands, now of course they could have gapless points to the other passive bands, then the system is going to be, then these two bands are going to be topological. So this is a very strong statement, basically stating that the lowest two bands in twisted bilayer are always topological. Now, what I want to do is find out, what we want to do is find out what type of topology do they have. And in order to do this, what you take is what's called the Berry phase calculation, where you basically take these two bands, compute their Berry phase, their non-abelian Berry phase, which is also called Wilson loop. So the Berry potential is a matrix, and you kind of take a path-ordered integral around one direction, and you plot it as a function of momentum in the other direction. Okay. Normally, this, I mean, not normally, basically in every case, generically, this is not a proof, but in any case that we tried, that anybody has tried to see whether these Wilson loops reveal the topology of the system, the answer has been yes. Okay, so for example, if you have a churn band, a single band, then the eigenvalues of this Wilson loop will basically wind. So this is a unitary operator who's got eigenvalues between 0 and 2 pi. They would wind as I move this momentum, okay? As I move this momentum, as I plot the eigenvalues versus this momentum. So I take the Wilson loop, or the integral of the Berry potential in this direction, plotted versus this direction here. They wind. For a quantum spin Hall system, where I have two bands at least, you'll see, the time reversal winding of the Vanier centers. These are two time reversal one Vanier center. This is a Kramer's-Jernsky, this is a Kramer's-Jerns, etc. Okay. So what you do is you take this for twisted bilayer and you do this, and in the regions where two bands are gapped from the other bands, the two active bands are gapped from the other bands, you get something that's basically topologically equivalent as winding to this. I'm going to go on for like 3 more minutes and then finish. It's topologically equivalent to this. You can see that they're basically more or less the same with some different, some wiggles around it. But you have a center that winds in one direction, and a center that winds in the other direction. So basically, kind of like a spin up in in magnetic field up, spin down, magnetic field down. So this looks very similar to this, to the quantum spin Hall, okay? But the symmetries are very different. One symmetry is time reversal, spinful time reversal for quantum spin Hall. One symmetry is spinless time reversal, C2Z times T, okay? So even though the Wilson loop looks the same, actually the Wilson eigenstates, the eigenstates of the Wilson loop are very different. And it was long thought that the topology of these bands would be what's called fragile, meaning the following thing. So whereas in a topological insulator, so the winding of the Wilson loop, I'll answer the question when I finish here. So whereas the winding in the Wilson loop of a topological insulator, these with time reversal, with spinful time reversal, these points are protected by Kramer's degeneracy, and adding bands to the system, you know, with Kramer's degeneracy would give you a Z2 classification. Here, adding bands to the system can make these two states trivial. That's not true if you keep all the symmetries, as I'll show you in a little bit. But basically, this is kind of like at the beginning, this was thought to be true. So if I have, these are the two active bands, okay? These crossings turn out to be protected not by time reversal, because I don't have time reversal in the single layer system, but by C2 times time reversal, okay? These crossings are protected by C2 times time reversal, and this crossing also. So they're locally stable. They can move around, but they're locally stable. But what I can do is add two more bands to the system. So I add two more trivial bands, just simple orbitals, just to stake and add two more simple trivial bands, and now do the Wilson calculation of the full 4 bands of the system. And it turns out that these crossings here are not protected, okay? That actually turns out, so they're not protected, so they can open a gap here, and then you can have no winding. So you can have a Wilson loop of 4 bands, which basically does something like this. And I think, as Neuper will point out from the abstract of his talks, this basically means no winding or no topology. So this means that the state, which was 2-band topological, when you add bands, when you add 2 bands, it can become trivial, okay? So this is the concept of fragile topology, and basically it tells you that if you add trivial Hilbert spaces to a non-trivial fragile topological problem, it can become trivial, okay? Now, I wanted to end with this slide. It turns out that actually, if you keep particle Hall symmetry, and this is the reason why I'm answering the question, why would you want to keep particle Hall symmetry? So this winding here of the 2 bands is all you need. Is you don't even need the crystalline symmetries. All you need for the winding of these 2 bands for making this classification is C2Z times T, okay? That's the only symmetry that you need, which basically protects these nodes in the Wilson loop. But what's usually beneficial is to use the full symmetry of the system and then ask, if I kill X, Y, and Z symmetries, okay, do I still have topology, or does the topology change? Okay, and it turns out that with particle Hall, if you maintain particle Hall, the topology is actually stable, not fragile. So this is something that I'll go through next time. But basically, there are several statements that I wanted to make. Statement number 1 is that particle Hall is actually good at low energies, and it provides stable topology. So in other words, the TBG in one valley is topologically anomalous for any number of bands. This is okay because you have a continuum model. You couldn't have this in a tight binding model, okay? Because the tight binding model has a bandwidth, and then if you took all the states in that bandwidth, all the bands together in a tight binding model have to be trivial because they're just the orbitals of the tight binding lattice. But here you have a continuum model, and in this continuum model, the there's no contradiction to all the bands being topological. For example, one continuum model where all the bands are topological is the surface of a three-dimensional topological insulator. On the surface of a three-dimensional topological insulator, no matter how many bands you take, all of them are topological. Now here, the interesting thing, so the surface of a topological insulator is anomalous. Now here, the interesting thing is that you have a two-dimensional model by itself that's anomalous. The difference is that it's a continuum model around one value. If I took the other value and added it in, it wouldn't be anomalous anymore. Okay, so I'll show you how that happens next time. And now I finish and take questions. Thank you. I actually cannot read the questions. Let's see. Oh, hang on 1 second. Okay.
I can read the questions.
Oh, I can read them too now. I just had like a technologically challenged moment. Okay, I can read the questions. So question number 1, can the lowest graphene band, so again, lowest means the ones around charge neutrality. So said by particle hole come from one branch of disconnected EBR or not? That's a good question. I would assume yes. Yes, I think yes. They can be a disconnected branch of an EBR. I think that's true. I think that's true, but don't quote me. In any case, you can go and check it immediately on the Bilbao crystallographic server. All for the symmetry group, all the EBRs are tabulated, and I think you're right. The answer is yes. Okay, next question. Does the EBR decomposition capture the weak nature of the TI? So this is, I mean, so it's a fragile nature. So first of all, the fact that here you don't have, let's see what it is. So the fact that there's no way you can write down these eigenvalues as compositions of elementary band representations, i.e. atomic limits, or also known as atomic limits, immediately shows you that it's topological. Now, if you squint, and I kind of like very quick to notice, more quick than I am, you'll see that you can write this down as not sums of atomic bands, but sums and differences. Okay, so that basically tells you that it's not strong topological. Now, all these, so again, so I kind of said then afterwards, I said, oh, but with particle it's topological. So why does it's strong topological at all bandwidths? So why don't they show up in this? Well, the Bilbao crystallographic server doesn't contain particle hole because particle hole is not a crystallographic symmetry. Particle hole is kind of a symmetry at low energies. It comes from the low-lying excitations of the Dirac fermions, and it's certainly not included as a crystallographic symmetry. It's included in an effective symmetry. Not being included in the crystallographic symmetry, this is outside of the theory, that Barry, Jen, Luis, Maya, and Zijun made. So basically, it wouldn't show up in these cases. If you have extra symmetries like particle hole, you'd have to add them up afterwards. So but that's good because that means you can find new stuff. Okay, I hope that was answered. Next question, can this be generalized to other systems with crossing, not necessarily Dirac at any point in the Brion zone? Yeah, it's a very good question. So can this type of argument be generalized to other systems? So for example, to other Moiré systems. So the full answer is I don't know. It's certainly a very good question. One could, possibly do it on the square lattice with some symmetries, which has a Dirac node at the corner. You can do a similar situation. you know, the special thing here is that, you know, this, if I just had C2Z symmetry, I would have fragile states. And, you know, in order to see that they're topological, I would have to compute the Wilson loop. Here, I can just do it from just eigenvalues because I have these you know, rules for how the eigenvalues of the bands work. So I guess you could do a similar thing if your system has eigenvalues and if, you know, your excitations are you know, that you start off are relatively easy, like a Dirac node, etc. If you start off with a large Fermi surface and then put 2 layers and twist, that becomes much more complicated because, you know, you have a lot of states. But if you just have a Dirac point like here, you know, the crucial thing about these arguments was the fact that, you know, I could go away from 0 coupling between layers to non-zero coupling. So I think, you know, Inigo, that's the answer to your question is that this is basically a research question. So I think it should be possible. And I think it would be very interesting to find out if it's possible to do it for other lattices. The downside of it is that, you know, not many people will care unless these lattices are experimentally foundable. So pick a lattice that, you know, people can do this twisting on. That's a very interesting question that should be answered. Okay. Does this fragile topology have quantum spin Hall effect? So it doesn't have quantum spin Hall effect in the sense of having edge states. Okay. So why is that? So I think Titus will, maybe Jen will talk about this. Certainly Titus from his abstract. Really the symmetry that protects this, you know, I can kill all the symmetries, and this fragile topology in the end is protected by just C2Z times T. I can kill all the other symmetries and I'll still have a protected state, okay, as long as I keep C2Z times T. Now, what's the difference between C2Z times T and just T? Well, first of all, for the quantum spin Hall effect, T for the quantum spin Hall effect is squares to -1, C2ZT for this case squares to 1, but that's, you know, one of the differences. The difference physically is that the time reversal for the quantum spin Hall effect keeps the edge invariant, okay? So it's a local symmetry. So if I cut the sample and make an edge, then time reversal acts locally on the edge, okay? So it has edge states. It's topological state going to the back and it has edge states. Now, C2Z times time reversal, if I make an edge, C2Z flips this edge to this edge. Okay, so C2Z, so the symmetry that protects the bulk being C2Z times T, once you make an edge, it flips one edge into the other. So an edge breaks locally C2Z times T symmetry. So you wouldn't expect edge states, and there's no edge states. But what there are corner states, as Titus will speak about. So basically, these two edge states, you know, if I, you know, for example, take a quantum spin Hall with C2Z and T, T squared equals to 1, then kill both C2Z and T, but keep C2Z times T, this edge would be mapped into this edge, and then at their intersection, kind of like a rhombohedra here at the intersection, you'd have corner states. So this is, you know, some sort of a higher order a topological system, as most fragile states are. Okay. Last question, I guess. I believe that, okay, not last question. I believe the fragile models are used to describe topological properties in TBG, and they obtain reasonable predictions related to topological properties in TBG, such as Chern states. Okay, so that's a comment, not a question. Okay, yes, I mean, the Bissett-McDowell model is used to make predictions, and that has stable topology because it's got particle Hall. Okay, so that was a comment. Can you say something about what happens when you couple K and K prime? Does it trivialize the bands? Yes, it does trivialize the bands, but what you have to remember is that the coupling between K and K prime is exponentially vanishingly small. There's some issue with the number of paths you can take, but in the end, it turns out that the coupling is exponentially small. Okay, so the coupling being exponentially small, if you add k and k prime, you trivialize the bands, but by an exponentially small amount. Okay, so you basically don't trivialize them. I mean, if I'm, if you were to couple them and add a significant term between them, then you trivialize them. But basically, because the coupling is very small physically, the trivialization, which would be measured by, if you'd couple k and k prime, you'd get twice this, and then you'd get a small gap here in the Wilson loop. But this gap would be vanishingly small, exponentially small. So really, you wouldn't get a trivialization. Okay, unless you add strong coupling between k and k prime, which is not physical. Okay, does it make sense? Any more questions?
Yes.
There's more questions. Okay, can you interpret the higher topology from the Wilson loop spectrum? Yes, you can certainly interpret it from the Wilson loop spectrum if you know the symmetry that protects the Wilson loop spectrum. So if I showed you just the Wilson loop spectrum, if I showed you just this, okay, so say you come to me and you say, oh, well, show me the Wilson loop, and I just showed you this, you wouldn't be able to distinguish it from this if you just saw the Wilson loop spectrum, okay? But the Wilson loop, also has eigenstates, for example. So this guy is not only eigenvalues, but also has eigenstates. And from the eigenstates, so if you give me the full Wilson loop, from the eigenstates, I would be able to tell you that the eigenstates are related to each other by c to z times t, and not by t. Okay, so I'd be able to tell you that it's not a quantum spin hole, but it's a c to z times t Wilson loop. Okay. Also generically, actually, this spectrum. So here, because I have extra symmetries, these are at 0 and pi. But if I just keep c to z times t, okay, generically the spectrum can look like this. Okay. So generically, with just c to z times t, with no other spatial symmetries, okay, the spectrum can, and this is continuous here, right? Okay, and this is a twofold degeneracy here too. So c to z times t keeps these degeneracies in the Wilson loop spectrum. Okay, it keeps them locally stable. Okay, but you can move them around, right? You can move them around. Whereas with time reversal, with a quantum spin Hall state, you cannot. Well, not that you cannot, but these are always degenerate at pi and 0. Okay, so with c to z times t, you can move these degeneracies away. Here they're at pi and 0 because of crystalline symmetries for this sample. If you kill the crystalline symmetries, you can move them. So in the generic case of c to z times t by itself, I would be able to tell you that this is not a quantum spin Hall state because it doesn't have degeneracies at k. If I keep spatial symmetries and get the degeneracies pinned in the Wilson loop at 0, at k equals 0 and pi, then I'll still be able to tell you that it's topological by looking at the eigenstates of the Wilson loop.
There is another question.
One-dimension finite. Well, I mean, I was considering a system with 2 dimensions, but the edge state not being a circle. Okay. If the edge state is not a circle, it's a rhombohedron, or like if the edge state does this, okay. The edge state does this. So sorry, I should read the question. You said C2ZT acts on the edge states by exchanging two edge states. I guess you're considering system with only one dimension finite. What happens if we take a system which is finite in 2 dimensions, so the edge might map into itself on C2ZT? So the edge doesn't map into itself on the C2ZT. That's, I mean, it's, well, depends. It's an issue of language. Okay, what we can say is that, you know, the edge, this point on the edge with C2Z times T never maps to itself. Okay, it maps to, for example, this point. Okay, and that's true no matter what dimension, what, you know, what shape or form the edge states have. So that means that locally you don't have a symmetry that to protect your edge states here. Okay, like in quantum spin Hall, you have time reversal, which protects edge states here, but locally you don't have. It means that the mass on this edge, I can open the gap on this edge. So say if I start off with gapless edge states, I can open a gap while maintaining C2Z symmetry, but the mass of this edge and the mass on this other edge would be opposite, and then you'd get corner states here. But Titus will explain this in great detail in his talks. More questions? Okay.
All right, if you have more questions, you can write them down on the Slack channel, and we can ask them tomorrow, we hope, before his next lecture. So thank you, Andre.
Very good.
Very nice talk.
Thank you so much.
And see you,
Thanks.
everybody, tomorrow.
Yeah.
Titus
Thanks.
is there too. He can maybe want to say hi.
Thank you. Bye.
Hi. Now I know at least what I have to talk about.
Sorry, I looked at your statement.
Oh, no, it's good. Yeah, it's great. Fantastic.
We'll be talking about it. Now it's like in politics, it's payback time.
Yeah, exactly.
If you say you leave country, you should you should not evacuate the embassy at the last moment. Okay, see you.
See you guys. Yeah. Bye-bye.
See you tomorrow. Bye-bye. I close the session now.